Did everything we know start from nothing? This question lies at the heart of our understanding of the universe. For as long as humans have existed, we have been curious about where everything came from. Philosophers have thought about the idea of nothing, while scientists look for clues in the stars and galaxies. How did the universe truly start? In cosmology, the term universe encompasses everything that exists, every galaxy, star, planet, and even the vast stretches of empty space between them. It includes all matter and energy, the laws of physics that govern their interactions, and the very fabric of space and time itself. Think of the universe as an enormous tapestry, woven together from countless threads of galaxies and cosmic structures. At its broadest level, the universe is not just what we can see or what is contained within our telescopes. It also includes regions beyond our observational reach, where light has not yet had time to travel to us since the beginning of the universe. This means there may be parts of the universe that remain invisible, hidden from our current understanding. The universe is also dynamic. It began with the Big Bang, a colossal explosion that marked the beginning of time and space. Since that moment, the universe has been expanding, stretching out in all directions. It continues to evolve, with galaxies moving apart from each other over vast distances. There are also concepts like dark matter and dark energy included in our understanding of the universe. Dark matter doesn't emit light or energy, making it invisible to our instruments. Yet it exerts a gravitational pull influencing the structure of the universe. Dark energy, on the other hand, seems to be responsible for the accelerated expansion of the universe, pushing galaxies further away from each other. In cosmology, studying the universe involves piecing together clues about its history, its structure, and the fundamental forces that shape its behavior, drawing a clearer picture of this remarkable cosmic expanse we inhabit. Throughout history, different cultures have looked up at the sky and created unique stories and beliefs about the universe. These perspectives were shaped by their environment, experiences, and the knowledge available to them at the time. In ancient Mesopotamia, for example, people viewed the night sky as a canvas painted with the lives of gods and goddesses. They believed celestial bodies had powerful influences over their fate, leading to complex systems of astrology that linked the movements of planets to earthly events. Similarly, ancient Egyptians associated the stars with their mythology. They built pyramids aligned with the stars, reflecting their belief that the heavens were a pathway to the afterlife. The stars represented gods and were crucial in their understanding of time and agriculture, particularly the annual flooding of the Nile River, which was linked to the star Sirius. In China, the cosmos was seen as a grand balance between opposing forces. The idea of yin and yang permeated their worldview, and the stars were part of a larger harmony. Traditional Chinese astrology focused on the cyclical nature of life, with celestial events directly influencing human affairs. Native American cultures also tell rich stories about the universe. Many tribes viewed the sky as a living entity, and constellations often symbolized important lessons, animals, or historical events, bridging the gap between the earthly realm and the spiritual. In contrast, Western traditions evolved differently. The Greeks laid the foundations for scientific inquiry, with figures like Aristotle and Ptolemy proposing models of the universe based on observation and reason. Their work influenced generations and helped transition humanity toward a more systematic understanding of celestial mechanics. These diverse interpretations of the universe reflect a wide array of beliefs and knowledge systems, enriching human culture and shaping our collective curiosity about the cosmos. Each perspective not only helped to explain the physical world, but also served to connect communities with their environment, guiding navigation, agriculture, and even moral lessons that have persisted through generations. The origin of the universe is a fundamental question that captivates both science and philosophy because it addresses the very nature of existence itself. At its core, this inquiry explores how everything we see around us came to be, from the vast galaxies down to the tiniest particles. Scientifically, this question leads us to theories like the Big Bang, which suggests that the universe began as an incredibly hot and dense point, expanding and cooling over billions of years to form stars and galaxies. This scientific exploration helps us understand the physical processes that govern the cosmos, providing a framework to describe the unfolding of our universe. Philosophically, the origin of the universe raises profound questions about causality and existence. What caused the universe to begin? Was there something before it, or did time itself start with the universe? These questions delve into the nature of reality and challenge our understanding of the beginning of everything. Philosophers often engage in discussions about whether the universe has purpose or meaning, and if so, what that might entail. This interplay between science and philosophy enriches our understanding, as each discipline poses questions that can inform and expand the other. Ultimately, the quest to understand our universe's origin isn't just about exploring the stars, it's about examining our place within it and contemplating the very essence of what it means to exist. This fusion of inquiry into science and philosophy invites us to ponder profound concepts about life, existence, and the universe's mysteries, making it an enduring and central question in human thought. Physicists have a unique perspective on the concept of nothing, especially when it comes to space and matter. In everyday conversation, nothing might imply an empty room or a void. However, in the realm of physics, it's a bit more complex. When scientists discuss nothing, they often refer to a space that contains absolutely no matter, not a single atom, molecule, or particle. Yet this idea of nothing is not completely devoid of significance. According to quantum theory, the very fabric of space itself can never be entirely empty. Even in a vacuum, where we think there is nothing, there are tiny fluctuations and virtual particles that pop into and out of existence. This is a process occurring constantly, suggesting that what we consider nothing is teeming with potential and activity at a microscopic level. Moreover, when physicists define nothing in terms of space, they also use the concept of a vacuum. This vacuum is a state with the lowest energy levels possible, where still certain forces might exist, affecting the space around it. In this context, nothing does not mean a complete absence of energy or forces. Instead, it refers to a state of minimal presence, where even the fabric of the universe is influenced by underlying principles. So, in the scientific world, nothing is a rich, dynamic state rather than an empty, meaningless void. It invites curiosity about the nature of existence itself and how the universe operates under the framework of both matter and emptiness. The concept of nothing has intrigued philosophers for centuries, leading to a variety of arguments and interpretations. At its core, nothing can be understood as the absence of anything: no matter, no energy, no space, and no time. This absence poses fundamental questions about existence itself. Some philosophers argue that nothingness cannot truly be conceived. They suggest that if we attempt to discuss nothing, we inevitably turn it into something. For instance, to say there is nothing means we must use words and concepts that imply an existence of a state or a condition. This paradox highlights a struggle with our understanding of reality and imagination. Others propose that nothing is a meaningful concept, crucial to discussions about existence. Thinkers in existentialism explore the idea that nothingness is fundamental to human experience. For example, they argue that in recognizing life's transient nature, moments that come and go, we encounter nothing in the sense that all things eventually cease to exist. This acknowledgement may lead individuals to find purpose or create meaning in their lives as they confront the impermanence of their experiences. In the realm of physics, the conversation shifts slightly with discussions around the vacuum of space. Some scientists note that even in absolute emptiness, vibrational energy and potential exist. This scientific observation feeds philosophical debates about whether this state truly equates to nothing, or rather represents a different kind of something. Additionally, the concept of nothing raises questions about creation itself. Some philosophical traditions argue that something cannot arise from nothing. This leads to discussions about the origins of the universe, with thinkers grappling with whether a creator is necessary to explain existence, or if the universe can be self-originating within a framework of rules or laws. Overall, the philosophical exploration of nothing invites profound contemplation, bridging ideas from metaphysics, existential thought, and even scientific inquiry. The ways we navigate these discussions illuminate not only the nature of existence, but also the limits of human understanding itself. In classical physics, the concept of nothing can often be viewed as an absence of matter or energy, a vacuum where nothing exists. For instance, when we talk about outer space, we think of vast regions with very little matter. In this framework, nothing essentially means empty space devoid of any particles or physical influences. It's a straightforward idea that leans heavily on our perception of the physical world as something made up of solid objects and forces acting upon them. However, the realm of quantum mechanics introduces a much more complex notion of nothing. In quantum theory, even in what we might think of as empty space, there are fluctuations and mysterious activities happening on a tiny scale. Picture nothing not as a void but as a rich field of potential. This vacuum state, while it seems empty, still contains energy and can give rise to virtual particles that pop in and out of existence. These particles do not stick around. They appear briefly before disappearing again, but their very presence indicates that empty space is teeming with activity. Furthermore, this quantum perspective allows for the idea that the universe is alive with possibilities, where truly nothing might not exist at all. Those fluctuations challenge our fundamental understanding, suggesting that even in emptiness, there are forces and interactions at play, creating a vibrant and dynamic backdrop rather than a true void. Thus, the difference between the classical and quantum views of nothing highlights a fascinating transition from a simplistic understanding of emptiness to a complex, ever-active environment that reshapes our view of existence itself. The concept of nothingness plays a fascinating role in many religious and spiritual beliefs, often serving as a gateway to deeper understanding and connection with the universe. In some traditions, nothingness is viewed as a state of pure potential, where existence itself has not yet taken form. This brings a sense of openness and possibility, suggesting that from nothing, everything can emerge. In Buddhist philosophy, nothingness can resonate with the idea of emptiness, known as sunyata, which denotes the absence of inherent existence. This perspective encourages followers to realize that attachment to material objects or identities can lead to suffering. Instead, by recognizing the ephemeral nature of life, practitioners are urged to embrace the fluidity of existence. In this light, nothingness is not seen as a void, but rather as a boundless state that allows for compassion, awareness, and enlightenment. In Western philosophical and theological contexts, nothingness often sparks discussions on creation and existence. For many monotheistic religions, the idea that the universe was formed from nothing by a divine being highlights the power of that creator. It emphasizes that the divine presence brings order, structure, and meaning to what might otherwise be chaos and emptiness. Furthermore, existential philosophies explore nothingness as a core element of human experience. The realization of mortality and the limitations of existence can lead individuals to question their purpose and the significance of life itself. This confrontation with nothingness inspires a quest for meaning, prompting a journey of self-discovery and engagement with both the spiritual and the material worlds. In many indigenous spiritual beliefs, nothingness may be intertwined with concepts of the void or the great mystery, which fosters a deep respect for life and nature. This acknowledgement of nothingness often leads to a harmonious relationship with the earth, viewing it as a vital part of the greater whole rather than something to dominate. Thus, nothingness transcends mere absence. It embodies the complexities of existence, urging seekers to explore the nuances of life, creation, and their place in the cosmos. Whether as an embrace of potential, a tool for enlightenment, or a pathway to understanding, this concept encourages profound introspection and connection to a greater reality that extends beyond the tangible. The Big Bang Theory is widely accepted as the best explanation for the universe's beginning, and several key pieces of evidence support this idea. One of the most compelling clues comes from the observation of cosmic background radiation. Imagine the universe shortly after its creation, filled with hot, glowing gas. As the universe expanded, it cooled down, and this now very faint glow can still be detected in every direction. It's like the afterglow of a once bright firework, lingering in the darkness of night. Another piece of evidence is the observed redshift of galaxies. When we look at distant galaxies, we notice that their light is shifted towards the red end of the spectrum. This means they are moving away from us, which suggests that the universe is expanding. If we were to trace this backward in time, it leads us to a singular starting point, much like peeling an onion, a moment when everything was condensed into a small, hot state. The abundance of light elements like hydrogen and helium also supports the Big Bang theory. In the first moments after the event, the universe was a hot environment where particles combined to form the simplest elements. The specific ratios of these elements found in the universe today match the predictions made by the theory, solidifying its credibility. Lastly, the large-scale structure of the universe, the way galaxies are distributed, is another important factor. Observations show that galaxies are not randomly scattered, but rather organized in filaments and clusters, which fits with computer simulations based on the Big Bang model. These simulations depict how matter would clump together over time from a hot, dense state, leading to the rich structure we observe today. Together, these pieces of evidence form a strong foundation that supports the Big Bang theory, painting a dynamic picture of the universe's origins from a singular explosive event to the vast cosmos we inhabit now. The concept of the Big Bang originated from a combination of observational evidence and theoretical exploration in the early 20th century. Scientists began to notice that galaxies were moving away from us, and this was observed through the phenomenon known as redshift. When light from distant galaxies travels to us, it stretches out, and this stretching indicates that those galaxies are receding. The farther away a galaxy is, the faster it's moving away, which leads to the idea that the universe is expanding. This expansion suggested that there must have been a starting point, a moment when the universe was smaller and denser. Belgian priest and physicist Georges Lemaitre was one of the first to propose a theory around this idea in the 1920s. He suggested that the universe began from a primeval atom, which concentrated all the matter and energy of the universe in an incredibly hot, dense state before it began to expand. The idea gained more traction with the work of Edwin Hubble, who, in the 1930s, provided concrete evidence to support Lemaitre's theory. Hubble's observations of galaxies showed a clear relationship between their distance and the speed at which they were moving away from Earth, confirming the expansion of the universe. As these ideas developed, scientists recognized that if the universe is expanding now, it must have begun in a hot, dense state. This notion was further solidified by the discovery of cosmic microwave background radiation in the mid-20th century. This radiation is considered a remnant heat from the early universe, like an afterglow of the Big Bang itself, hinting at the conditions just after the universe began. All these pieces came together to form a coherent picture. The Big Bang theory describes not just the existence of an expanding universe, but also provides a timeline of events leading from that incredibly hot, dense beginning to the vast, cooler cosmos we observe today. The evidence continues to grow, making the Big Bang one of the most widely accepted explanations of the universe's origin. The Big Bang theory describes the very beginning of our universe as a moment of extreme density and temperature. Imagine everything in existence compressed into a tiny point, infinitely small and incredibly hot. Around 14 billion years ago, this point began to rapidly expand. In the first moments after the explosion, the universe was a chaotic mix of energy and particles. As it expanded, it cooled down enough for particles like protons, neutrons, and electrons to form. During this stage, the universe was primarily made up of light elements such as hydrogen and helium. As time progressed, approximately 3 minutes after the Big Bang, the temperature had cooled sufficiently for these particles to combine and form the first atomic nuclei. This process is referred to as nucleosynthesis. However, the universe was still too hot for atoms to hold together, so it wasn't until about 380,000 years later that the universe cooled enough for electrons to combine with nuclei and form neutral atoms, an event known as recombination. This moment allowed light to travel freely for the first time, leading to the release of what we now identify as the cosmic microwave background radiation. This faint glow can still be detected today, providing a snapshot of the universe when it was just a young, hot, and dense place. Over millions of years, gravitational forces began to pull matter together, forming the first stars and galaxies, setting the stage for the vast and complex universe we observe now. Each of these steps molded the universe into its current state, creating the conditions necessary for the formation of planets, stars, and eventually life. Cosmic microwave background radiation, often referred to as CMB, serves a crucial role in our comprehension of the Big Bang theory. To understand this, envision the universe shortly after its birth, roughly 13.8 billion years ago. During that initial moment, the universe was incredibly hot and dense. As it expanded, the temperatures began to cool. Imagine the transformation occurring as the universe stretched and evolved. About 380,000 years after the Big Bang, the temperature had cooled enough for protons and electrons to combine and form hydrogen atoms. This moment is akin to the universe becoming transparent. Suddenly, light could travel freely throughout space instead of being trapped in the hot, dense fog of particles. The radiation emitted at that time is what we now detect as CMB. It fills the universe uniformly and is a faint glow that we can capture with sensitive instruments. This glow comes from the remnants of that hot, dense state and is a critical piece of evidence for the Big Bang. Detecting this radiation provides scientists with a snapshot of the universe when it first became transparent and helps establish how it has expanded and cooled over billions of years. Studying CMB allows scientists to uncover vital information about the universe's age, composition, and rate of expansion. It reveals small fluctuations in temperature across the background that correspond to variations in density, which seeded the formation of galaxies. Thus, CMB acts as a cosmic fingerprint, providing insights into the early universe and laying down the foundation for understanding how everything we see today came to be. Quantum fluctuations are fascinating phenomena that suggest our universe might have originated from a state of nothingness. To understand this, imagine a calm, empty space where no matter and energy exist. Quantum mechanics, which governs the behavior of the tiniest particles, reveals that even this seemingly empty space is alive with energy and activity at the smallest scales. These fluctuations mean that particles can momentarily appear and disappear, just showing up out of nowhere before vanishing again. It's as if an invisible ocean of energy is bubbling just beneath the surface. This transient activity hints at a potential mechanism for creation. In this context, nothing is not truly devoid of possibility. Instead, it is filled with potential energy waiting to manifest. If conditions are just right, one of these fleeting fluctuations could become stable, leading to the formation of matter and energy. Picture a tiny ripple in that ocean growing until it becomes a wave. This wave represents the birth of something significant, possibly the beginning of our universe. As these fluctuations create particles, they can lead to the gradual evolution of matter, eventually forming stars, galaxies, and everything we see today. So rather than originating from absolute nothingness, the universe might have emerged from a dynamic, fluctuating state, an energetic tapestry where the potential for existence constantly churns. This perspective invites us to rethink our ideas about creation and the origins of everything in remarkable ways. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that reveals a fascinating aspect of the universe. It states that we cannot simultaneously know both the exact position and momentum of a particle. Imagine trying to track a tiny, buzzing insect in a dimly lit room. The more precisely you try to measure where the insect is at that moment, the less certain you become about how fast it is moving. Conversely, if you focus on measuring its speed, its exact location becomes unclear. This principle is significant because it highlights the inherently unpredictable nature of the quantum world. At small scales, particles like electrons pop in and out of existence and behave more like waves than solid objects. This behavior leads to what are termed quantum fluctuations, temporary changes in the energy levels of empty space that can produce pairs of particles that exist for an incredibly brief time before disappearing again. These fluctuations are more than just theoretical curiosities. They play a crucial role in many physical processes. For instance, they are thought to contribute to the formation of the universe during the Big Bang, where small energy fluctuations could lead to the large structures we see today. Furthermore, they challenge our classical understanding of reality, indicating that uncertainty and probability are foundational to the behavior of even the smallest particles. The Heisenberg uncertainty principle, therefore, not only reshapes our understanding of particles, but also intertwines with the cosmic tapestry of existence itself, making the study of the quantum realm ever more captivating. Virtual particles are fascinating entities in the realm of quantum physics. They are temporary fluctuations that appear and disappear in empty space, almost like tiny bubbles in a vast ocean. This might sound abstract, but these particles can have real implications for understanding how the universe began. In the earliest moments after the Big Bang, when the universe was extremely hot and dense, the laws of physics operated differently than they do today. During this time, conditions were ripe for virtual particles to emerge spontaneously. These fleeting particles could effectively pop in and out of existence, creating a dynamic and turbulent environment. The concept of virtual particles ties directly into the idea of energy fluctuations in a vacuum. This means that even what we perceive as empty space is teeming with potential energy. When conditions are just right, such as in the mind-bending scenario right after the Big Bang, these fluctuations might have contributed to a significant release of energy. This energy could, theoretically, lead to the creation of real particles, giving rise to the matter and antimatter that we observe in the universe. As the universe expanded and cooled, the balance between particles and antiparticles shifted, allowing some matter to remain while the rest annihilated with its counterparts. This event marks a key transition in the universe's evolution. Thus, virtual particles not only showcase the bizarre nature of quantum mechanics, but also serve as a bridge to understanding the birth of our universe. They hint at how energy fluctuations might have sparked the processes that led to the formation of everything we see around us today. The multiverse is a fascinating idea suggesting that our universe might be just one of many, perhaps even an infinite number of universes existing simultaneously. To understand this concept, imagine a vast library filled with countless books. Each book represents a different universe, each with its own unique set of physical laws, constants, and histories. In this library, some books might closely resemble ours, while others could be completely different, with alternate versions of reality, time, and space. This concept ties to the origin of our universe in intriguing ways. Our universe began with an event known as the Big Bang, which represents an incredible expansion from a state of extreme density and temperature. Some scientists theorize that this explosive moment could have been just one scenario within a broader multiverse framework. Various theories in physics hint that our universe's birth might be linked to other budding universes, perhaps through processes like cosmic inflation, where tiny fluctuations led to different regions of space-time expanding in unpredictable ways. Thus, while we see our universe as the only one we experience, the idea of the multiverse opens up possibilities that go beyond our current understanding. It invites us to consider how different rules may govern different universes and how they might interact or remain completely isolated from one another. This notion is both exciting and perplexing, challenging our views and encouraging a deeper exploration of what lies beyond the observable cosmos. The idea of a multiverse suggests that our universe may be just one of many, each with its own set of physical laws and properties. To understand how universes could emerge from nothing, we need to consider what nothing really means in this context. In physics, nothing doesn't necessarily imply a complete absence of existence. Instead, it can refer to a state where conventional matter and energy, as we understand them, are absent. Imagine a kind of energetic foam that fills the void of the cosmos. In this sea of nothingness, tiny fluctuations are constantly happening. These fluctuations can create brief, unstable pockets that could expand and evolve into a universe. When we talk about the birth of a universe, it may occur through one of these fluctuations that becomes stable enough to persist and grow. This means that conditions in the multiverse can allow for the spontaneous creation of universes from a kind of quantum energy state. Each of these emerging universes could have different laws of physics, leading to diverse outcomes. Some might resemble our own, while others could be completely different. The multiverse concept embraces the idea that countless universes can arise from a complex and dynamic void. Each fluctuation represents a unique opportunity for a new universe to form, filled with its own mysteries and potential. Thus, what might seem like nothing is actually a fertile ground for infinite possibilities, where the emergence of universes becomes a fundamental aspect of reality. The concept of a multiverse raises intriguing possibilities but also presents notable challenges for scientists. At its core, a multiverse suggests that our universe is just one of many, each potentially with different physical laws or constants. The first challenge is that the multiverse is inherently difficult to observe. Scientists primarily rely on evidence that can be measured or seen. Since other universes may not interact with ours, proving their existence becomes a nearly impossible task using traditional scientific methods. Another significant aspect is the problem of testability. In science, a theory is valuable when it can be tested and potentially proven wrong. If the multiverse theory cannot be tested by experiments or observations, it remains more of a philosophical idea than a scientific theory. Without tangible evidence, critics argue that it may not hold the same status as theories that can be observed and verified. Additionally, the multiverse concept can stall scientific inquiry due to its sheer complexity. The theoretical frameworks underpinning it, like string theory or cosmic inflation, are themselves intricate and often not well understood. Researchers grapple with how to connect these complex ideas with observable phenomena, which adds layers of difficulty in validating or refuting the multiverse theory. Finally, there are also philosophical challenges. The implications of a multiverse intersect with concepts of reality and existence. They force us to ask fundamental questions about our place in the cosmos and how we define what is real. These considerations stretch beyond empirical science into realms of speculation, causing debate about the nature of truth in a potentially infinite set of universes. As such, while the notion of a multiverse captivates the imagination, its validation or refutation remains a formidable task intertwined with profound scientific and philosophical questions. The concept of a universe emerging from nothing offers a fascinating perspective on how gravity fits into our understanding of the cosmos. To grasp this idea, imagine the universe in its earliest moments as a blank canvas. It was devoid of matter and energy, yet it somehow transformed into the vast, complex space we know today. Gravity plays a pivotal role in this transition. It is one of the fundamental forces in nature and exists wherever mass is present. When we think about nothing, it might lead to the question of what allows something to emerge from it. Here, gravity can act like a sculptor of the universe's fabric. While the universe started empty, quantum physics suggests that tiny fluctuations could have occurred, creating brief instances where particles spontaneously appeared and vanished. These fluctuations could be viewed as ripples on that blank canvas. Once gravity is introduced, it has the unique ability to pull together these tiny particles and energy into clumps, leading to the formation of stars, planets, and galaxies. Without gravity, the matter created from these fluctuations would have dispersed, preventing the formation of structure. In this sense, gravity not only challenged the idea of nothing because it required something like particles to exert force upon, but it also supported the notion by driving the organization and evolution of the universe from a non-existent state into a complex, structured reality. Ultimately, the interplay between gravity and the nascent matter could suggest a pathway whereby nothing becomes a fertile ground for creation, setting the stage for the vast universe that exists today. This relationship invites a deeper inquiry into what nothing really means in the context of the universe, as gravity offers a potential mechanism for turning absence into presence. Loop quantum gravity offers a fascinating approach to understanding the universe's inception. This theory starts with the idea that space and time are not smooth, continuous entities. Instead, they are made up of tiny, indivisible units, much like how matter is composed of atoms. Within this framework, the fabric of space-time is woven together from these little loops, creating a kind of network. When scientists think about the beginning of the universe, they often look at the moment known as the Big Bang. Traditionally, this theory suggests a singular point where everything started, but loop quantum gravity proposes a different perspective. It suggests that instead of a single explosion from a point, the universe may have undergone a series of events in which the compression of space reached a critical limit, leading to a bounce rather than a collapse. Imagine inflating a balloon. As the balloon expands at some point, it has to stop before it bursts. In a similar way, loop quantum gravity suggests that as the universe contracted under its own gravity, it reached a stage where it couldn't collapse any further. This critical moment could lead to a rebirth, the Big Bounce, where the universe ended its contraction and began expanding again, shaping the cosmos as we know it. This theory challenges the idea of singularities, where density and gravity become infinite. Instead, loop quantum gravity presents a framework where the laws of physics remain intact, providing a smooth transition from one state of the universe to another. This perspective not only sheds light on the universe's origin, but also invites scientists to explore the fundamental nature of reality, pushing the boundaries of our understanding of time and space. String theory introduces a fascinating perspective on the beginnings of the universe. It suggests that the fundamental building blocks of everything we see are not just tiny particles, but rather one-dimensional objects known as strings. These strings vibrate in various modes, and the way they oscillate determines the properties of particles like mass and charge. When considering how the universe began, string theory posits that prior to the Big Bang, our universe existed in a different state, possibly called a brane. This brane is a higher dimensional surface where strings reside. The theory imagines an event where branes collided or interacted, creating an immense release of energy. This colossal event could have sparked the Big Bang, leading to the expansion of our universe. In this view, the universe isn't just a simple explosive point. It's the result of intricate shapes and dimensions interacting in ways that still hold many mysteries. Such an interaction could result in the rich tapestry of galaxies, stars, and planets that fill our cosmos today. String theory encourages us to think of the universe as a complex system of relations between these strings and the dimensional spaces they occupy, offering a deep and interconnected fabric of reality that started from an astonishing point of cosmic change. String theory presents a fascinating perspective on the concept of nothing. In this framework, nothing isn't simply a void or absence, but rather a complex landscape of potential. Instead of viewing space as empty, string theory posits that at the most fundamental level, the universe is made up of tiny, vibrating strings. These strings can exist in different forms and vibrations, giving rise to all known particles and forces. Now consider nothing as the backdrop for these strings. In string theory, the vacuum, or what might seem like empty space, is actually teeming with these fluctuations, where strings constantly change and interact. This idea suggests that nothing is never truly the absence of substance. Instead, it is a dynamic state filled with possibilities. In this light, even in what seems like stillness, the fabric of reality is alive with energy and potential interactions waiting to emerge. Hence, the incorporation of nothing in string theory challenges our traditional understanding of emptiness. Rather than being devoid of content, the vacuum is a vital player in the universe, influencing how strings evolve and interact. This perspective opens up new dimensions of thinking, showing that even from nothing, the richness of the universe can arise. Branes, short for membranes, are fascinating concepts in theoretical physics, particularly in string theory. Imagine the universe as a vast ocean where different kinds of waves ripple across a surface. In this analogy, branes are like the surfaces or sheets floating within that ocean. They can take various forms, such as one-dimensional strings or higher-dimensional surfaces that can stretch across multiple dimensions. In string theory, it's believed that particles are not tiny points, but rather tiny vibrating strings. Branes are closely linked to these strings, providing a framework where they can vibrate and interact. This interaction can have profound implications for the origins of universes. Now think about how two branes can exist in close proximity in this higher dimensional space. According to some theories, when these branes collide, it could trigger an extraordinary event. This collision may create the conditions necessary for a new universe to emerge, similar to how a spark might ignite a fire. This event could lead to a Big Bang, where energy and matter burst into existence, forming a new universe with its own unique properties. This brane collision theory posits that our universe could be just one of many, all accessed through these interconnected branes. Each time a collision occurs, a new universe could be born, branching out into its own precious reality. Thus, branes provide not only a compelling way to think about the structure of our universe, but also a possible explanation for how universes might come into being in the grand tapestry of the cosmos. The concept of the universe beginning from nothing opens up a fascinating discussion in philosophy and science. At its core, the idea suggests that before the universe existed, there was no space, no time, and no matter. Essentially, there was absolute emptiness. This notion challenges our understanding of existence itself. One philosophical argument is the idea of causality, which asserts that everything that exists must have a cause. If the universe emerged from nothing, this seems to defy our everyday experiences of cause and effect. Philosophers like Aristotle believed in an eternal universe that always existed, while others argue that something must have initiated the creation, even if it was nothing itself. This pushes us to reconsider the definition of nothing and whether it can truly exist without something to give it context. Another argument focuses on the nature of existence. If we accept that the universe can emerge from nothing, it raises questions about the nature of reality and what it means to exist. Some philosophers posit that if nothing can produce something, then there might be more complex layers of existence we don't yet comprehend. This could hint at a multiverse, where our universe is just one of many that fluctuate in and out of existence. The problem of the first cause also plays a prominent role in this topic. Some thinkers, such as Thomas Aquinas, proposed that there must be an initial cause that sets everything into motion. If the universe began from nothing, proponents of this argument might insist that there must be a cause or reason behind this creation. This redirects the conversation back towards the fundamental questions of existence and the nature of the origin of everything we observe. In contemporary discussions, some atheistic viewpoints argue that the universe could have spontaneously arisen from quantum fluctuations, suggesting that nothing may not be as simple as it seems. On the philosophical side, this idea sparks debates about the nature of probability and the role of chance in existence. Ultimately, these philosophical arguments encourage an exploration of concepts that stretch our understanding of reality, existence, and the very fabric of the universe. Each perspective invites us to ponder deeper questions about why there is something rather than nothing, making the mystery of the universe's origin a captivating blend of philosophy and science. Existential philosophy offers a unique lens through which we can explore the universe's origin, particularly the concept of coming from nothing. At its core, this philosophy emphasizes individual experience, freedom, and the inherent meaning people seek amidst an indifferent universe. In this context, the idea of nothing becomes a profound and thought-provoking concept. Existentialists often argue that if the universe emerged from nothing, it highlights the absurdity of existence. Consider that nothing implies a lack of meaning, structure, or purpose. From this standpoint, the universe's origin does not come with inherent explanations or values. Rather, it enters existence without a preordained significance. This void invites us to reflect on our own existence and question our place within a vast, potentially chaotic cosmos. As we contemplate this, it becomes clear that humans have an innate desire to find meaning and understanding in life. The realization that the universe could arise from a state of nothingness can evoke feelings of existential dread or liberation. While the cosmos itself may be indifferent, it is up to each individual to derive their own meaning and to live authentically, despite the seemingly random nature of existence. Existential philosophy encourages us to embrace the uncertainty of our origins. It reminds us that rather than seeking answers from the universe, we should focus on our experiences and choices. By doing so, we create our own meaning in a world that, at its origin, came from nothing. This perspective fosters a sense of empowerment, allowing individuals to navigate their existence through personal freedom and responsibility in a universe that does not inherently provide answers. The concept of creation ex nihilo, which means creation out of nothing, has fascinated thinkers across various philosophical schools. Each tradition presents a unique perspective that reflects its deeper beliefs about existence, the universe, and the divine. In the Judeo-Christian tradition, creation ex nihilo is central. This view suggests that a divine being created the universe freely and purposefully from nothing, not from pre-existing materials. This idea emphasizes the sovereignty and power of God, positioning creation as an intentional act rather than a reaction to something already existing. Philosophers in this tradition often consider this act as a demonstration of divine will and creativity. Contrastingly, some Eastern philosophies, like certain strands of Hinduism and Buddhism, approach creation differently. In these views, reality is often seen as cyclical rather than linear. creation is typically viewed as an ongoing process where the universe undergoes cycles of creation and dissolution. The idea of nothingness holds different meanings here. It's often tied to concepts of illusion or Maya, suggesting that what we perceive as reality is ever-changing and ultimately insubstantial. In ancient Greek philosophy, thinkers like Plato viewed reality through the lens of forms and ideals. For Plato, creation could be an act of organizing pre-existing chaos into a structured cosmos, rather than originating from nothing. His ideas emphasize the existence of a higher world of forms from which material reality derives its meaning. Meanwhile, in secular philosophies and modern metaphysics, some might argue against creation ex nihilo altogether, positing that reality has always existed in some form or another. Thinkers in this vein explore concepts of infinity, suggesting that the universe may have always been here, eternal and uncaused, rather than being created. Each of these philosophical perspectives enriches our understanding of existence and the nature of creation. They invite us to ponder profound questions about the beginnings of everything we observe and our place within this vast tapestry of thought. This multifaceted discourse not only reflects our diverse beliefs, but also encourages deeper contemplation of the mysterious origins of the universe and our own existence within it. The concepts of dark energy and dark matter are essential to understanding the universe's formation and overall structure. Let's start with dark matter, which makes up a substantial portion of the universe's total mass. Though we can't see it directly, dark matter behaves like an invisible scaffolding, exerting gravitational forces that help hold galaxies and galaxy clusters together. Imagine a spider's web. Dark matter is the unseen strands of that web, providing stability and structure to the visible components of the universe. Its gravitational pull can influence how stars and galaxies are formed, shaping the universe from the very start. On the other hand, dark energy is an even more mysterious force that is causing the universe to expand at an accelerating rate. Think of dark energy as the energy of empty space. As space stretches, dark energy pushes outward, creating a kind of cosmic tension. This process plays a crucial role in the fate of the universe and its growth over time. If we envision the early universe as an extremely small and hot point, the rapid expansion that began with the Big Bang was influenced by whatever dominated that environment, perhaps a form of energy we categorize as dark energy today. When we say the universe formed from nothing, we refer to a state without matter or conventional energy. However, in quantum mechanics, true nothingness is tricky. The concept allows fluctuations where energy can spontaneously appear and disappear. These fluctuations might have seeded the initial moments of the universe, setting everything in motion. As the universe expanded, dark energy and dark matter shaped its evolution. As matter clumped together under gravity, forming stars and galaxies, dark energy continued to act against gravitational pull, dictating how structures grow and how quickly they can form. Thus, both dark energy and dark matter are intertwined in a fundamental way, influencing not just how the universe began, but how it continues to evolve, transforming what could have been an empty void into the rich, structured cosmos we see today. Incorporating dark energy into theories of the universe's origin presents several significant challenges for scientists and astronomers. First, it's important to understand that dark energy is a mysterious force driving the universe's accelerating expansion. It makes up a substantial portion of our universe, yet we know very little about its true nature. One major challenge is that dark energy does not fit neatly into existing physical theories. Traditional models of the universe, such as the Big Bang theory, struggle to account for how dark energy came into existence. While scientists have a good grasp of the universe's early moments, just after the Big Bang, they lack a clear explanation for how dark energy emerged and began to influence the universe's growth over time. This gap leaves a considerable hole in our understanding of cosmic history. Another complexity arises from the measurement of dark energy's effects. Observing its influence on the universe's expansion requires precise data on cosmic distances and the rate of that expansion. However, the universe is incredibly vast and filled with intricate structures that can obscure our measurements. A minor error can propagate into significant misunderstandings about how dark energy operates. Moreover, dark energy seems to behave differently in different contexts. For instance, Its effects on large astronomical scales might differ from its influence on smaller scales, complicating theories about how it interacts with other components of the universe, like galaxies and dark matter. These discrepancies make it difficult to create a unified theory that incorporates all these elements. Lastly, there is the challenge of coming up with testable predictions. Effective scientific theories should generate ideas that researchers can test and validate through observation. However, dark energy remains elusive, adding layers of difficulty to framing hypotheses that can be confirmed. As scientists delve deeper into the cosmos, they strive not just to understand dark energy, but to create models that resonate with both observational evidence and our current understanding of physics. This ongoing quest for knowledge underscores the complexity of weaving dark energy into the fabric of our understanding of the universe's origins. At the very beginning of the universe, immediately after its creation, everything was extremely hot and dense, far beyond anything we can experience today. Imagine a tiny point that was filled with unimaginable energy. This point then expanded very rapidly in a process we call the Big Bang. During this moment, space itself began to stretch and grow, much like blowing up a balloon. As this expansion occurred, the universe started to cool down quickly. In that hot, primordial soup, tiny particles began to form. Protons and neutrons, the building blocks of atomic nuclei, emerged as the temperature plummeted. Soon after, these particles began to combine and forge the first atoms, primarily hydrogen and helium, as the universe continued to expand and cool. This early phase, called the recombination epoch, saw the universe become less opaque. Light that was trapped in this hot soup could finally escape, allowing radiation to travel freely. This shift occurred around 300,000 years after the initial explosion. The light released then is what we now detect as the cosmic microwave background radiation, a faint glow that fills the universe and serves as a snapshot of that moment in time. As the universe continued to evolve, gravity began to play a crucial role in pulling matter together. Over millions of years, this clustering eventually led to the formation of stars and galaxies, creating the diverse and vast cosmos we observe today. Understanding this early stage helps scientists piece together the very history of everything, illuminating the profound journey from a singular moment of creation to the complex universe we explore now. The origins of the universe are described through an event known as the Big Bang, which occurred approximately 14 billion years ago. At this moment, the universe began as a singular point, extremely hot and dense, and then rapidly expanded and cooled. As it expanded, the energy present began to transform into the simplest forms of matter. Initially, in those first moments, the universe was composed of fundamental particles, such as quarks and electrons. Quarks are tiny particles that combine to form protons and neutrons, which then create atoms. These interactions during the cooling phase allowed these particles to form the basic building blocks of matter. As the universe continued to cool, protons and neutrons combined to create light elements, primarily hydrogen and helium. This process is known as nuclear fusion and took place during the first few minutes after the Big Bang. The conditions were also right for the formation of fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces, each one shaping how particles would interact with one another. These theories are supported by observations and experiments, such as the measurement of cosmic background radiation, which reveals remnants of the early universe and provides insight into its initial condition. This understanding forms the basis of what we know about the early universe and the emergence of the forces and particles that ultimately led to the complexity we observe today in everything from galaxies to life itself. Inflationary models explain how the universe went through a period of extremely rapid expansion just after the Big Bang. Think of the universe as a balloon. In its early moments, this balloon, representing the universe, was very small and tightly packed. Inflation suggests that in a fraction of a second, this tiny balloon inflated enormously, expanding faster than the speed of light. During this brief period, the universe grew exponentially, meaning it got much bigger in just a tiny amount of time. This rapid expansion helped to smooth out any irregularities or clumps of matter, much like how blowing up a balloon makes any wrinkles in the surface disappear. As a result, the universe became incredibly uniform, leading to the large-scale structure we observe today. This concept is crucial because it explains why the universe appears homogeneous on a grand scale, despite containing variations like galaxies and clusters. Inflationary models also predict certain patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, that scientists can measure today. These measurements provide strong evidence for inflation, supporting the idea that our universe underwent this extraordinary expansion phase in its infancy. Theoretical physicists use mathematics as a fundamental tool to create models that describe the universe's origins. Picture mathematics as a precise language that allows them to express complex ideas clearly. At the start of their explorations, physicists focus on the very first moments after the Big Bang, where all of existence began from an incredibly small and hot state. To understand this early universe, they rely on several key concepts like space, time, energy, and gravity. By applying equations that describe how these elements behave, physicists can simulate conditions in the universe just fractions of a second after its inception. Often these equations involve concepts like expansion and density, helping scientists predict how the universe evolved from that initial state. One of the essential frameworks they use is called general relativity, which describes how mass and energy influence the curvature of space and time. In simpler terms, mass can bend the fabric of the universe. This theory allows physicists to predict how the universe expanded and cooled, leading to the formation of galaxies, stars, and other structures we see today. In addition to general relativity, quantum mechanics plays a vital role as it helps explain the behavior of particles in those primordial conditions. The interplay between these two frameworks allows scientists to model everything from energy fluctuations to the creation of matter itself during those earliest moments. By running complex mathematical simulations and calculations, physicists can visualize scenarios and test hypotheses about the universe's beginnings. These models help reveal not just what happened, but also answer fundamental questions about why the universe is structured the way it is today. Through this intricate dance of math and physics, they aim to uncover the secrets of our cosmic origins. Describing a universe that begins from nothing presents intriguing mathematical challenges. First, we have to clarify what we mean by nothing. It is not just an absence of matter. It implies a state where even the laws of physics may not exist in their usual forms. This initial condition leads to many questions regarding how to frame physical laws when there is no established framework to use. One major challenge is understanding how something can arise from nothing without a specific cause. Traditional concepts in physics often rely on a cause and effect sequence, but in a scenario of nothing, this sequence breaks down. This leads to difficulty in applying mathematical models, which often depend on established quantities such as energy, space, and time. When starting from a void, these quantities lack defined values, posing a problem when trying to describe transitions to a state where the universe begins to form. Next, there's the issue of singularities. In cosmology, a singularity is a point where certain physical quantities become infinite or undefined, such as density being infinitely large at the moment of the Big Bang. Mathematically, working with infinities is problematic, as they can distort equations and yield non-physical results, further complicating any attempts to describe a transition from nothing to something. Moreover, quantum mechanics introduces another layer of complexity. In quantum theory, particles can spontaneously appear and disappear, challenging our notions of stability and being. This phenomenon suggests that the universe could stem from quantum fluctuations, but representing these fluctuations accurately in mathematical terms is no simple task. It requires balancing probabilities and understanding complex interactions on an incredibly small scale. Finally, when theorizing about cosmological models, researchers often employ advanced areas of mathematics like geometry and topology. The relationship between the shape of space and the dynamics of the universe adds further challenges to formulating equations. Each approach comes with its own set of profound implications and potential paradoxes that must be resolved to establish a coherent theory. Describing a universe that springs forth from nothing leads to significant mathematical hurdles, including redefining fundamental concepts, addressing singularities, grappling with quantum mechanics, and navigating the complexities of geometry. Each of these challenges reveals just how profound and intricate our understanding of the universe truly is. Astronomers gather evidence about the universe's beginnings through a combination of observational data, theoretical models, and advanced technology. One of the key pieces of evidence comes from the study of cosmic microwave background radiation, which is the afterglow from the early moments after the universe was formed. This radiation fills the universe and provides a snapshot of its state just a few 100,000 years after the Big Bang, offering insights into its temperature, density, and structure. Another important method involves observing distant galaxies and their movement. Due to the expansion of the universe, galaxies are moving away from us, and the light they emit is redshifted. By measuring this shift, astronomers can determine how fast these galaxies are receding, which helps estimate how long the universe has been expanding since it first began. This expansion supports the Big Bang theory, the dominant explanation for the universe's origin. Additionally, astronomers utilize computer simulations to recreate conditions of the early universe. These models are based on our understanding of physics and the known forces at play. By comparing the results of such simulations with actual observations, like the distribution of galaxies and cosmic structures, they can assess the validity of their theories about how the universe began. Finally, the study of elemental abundances in old stars provides more clues. The ratios of elements like hydrogen, helium, and lithium are tracked as they were created during the universe's early moments. Understanding how these elements formed helps piece together the chronology of the universe's expansion and evolution. Through this combination of observations, theoretical models, and technological advancements, astronomers build a comprehensive understanding of how the universe started and has changed over billions of years. To explore the early universe, scientists rely on advanced technologies that push the boundaries of our understanding. One of the most significant tools is the use of powerful telescopes designed to capture the faintest light from cosmic events that happened billions of years ago. These telescopes can detect radiation in various wavelengths, including infrared and radio. By observing in different ranges, they unlock new information about the formation of the first stars and galaxies. Another exciting technology is the development of sensitive detectors that help capture cosmic microwave background radiation. This radiation is a remnant from the Big Bang and provides a snapshot of the universe when it was just a young, hot, and dense state. By analyzing this faint glow, scientists can glean insights about the universe's composition, age, and evolution. Computational power also plays a crucial role. Using sophisticated simulations, researchers create models of the universe's development, allowing them to test hypotheses about how matter and energy interacted in its infancy. These computer models can visualize complex processes, helping scientists understand how structures like galaxies formed over time. Additionally, gravitational wave detectors have revolutionized our understanding of cosmic events. When massive celestial bodies like black holes or neutron stars collide, they produce ripples in space-time. Detecting these waves opens a new window into the universe, allowing scientists to learn about events that occurred in the early universe which would otherwise be invisible. Space missions equipped with innovative instruments are also key. For instance, specialized satellites can observe cosmic phenomena without interference from Earth's atmosphere. This enables clearer and more precise measurements, essential for studying the universe's origins. Through these cutting-edge technologies, scientists are piecing together the puzzle of how our universe came to be, revealing fascinating insights about its very first moments. Each discovery brings us a little closer to understanding the vast, dynamic cosmos in which we live. When we think about the origin of the universe, most of us recall the Big Bang theory, which describes the universe starting from an incredibly hot and dense state. However, there are several lesser-known theories that explore different possibilities for how everything began. One intriguing idea is the concept of a cyclic universe. Here, the universe undergoes endless cycles of expansion and contraction. Imagine blowing up a balloon. It expands until a point where it can no longer stretch and then starts to deflate. According to this theory, the universe could expand to a point, then collapse back into a hot, dense state, only to explode again in another Big Bang. This concept suggests that time could stretch infinitely in both directions, with no clear beginning or end. Another speculative theory involves the idea of a multiverse, which proposes that our universe is just one of many. Instead of being the only universe, imagine a vast sea of bubble-like universes, each with its own laws of physics and unique characteristics. Some might be similar to ours, while others could operate on entirely different principles. This idea challenges our understanding and raises questions about how different realities could exist simultaneously. The holographic principle is another fascinating viewpoint. This theory suggests that all the information contained in a volume of space can be represented as a two-dimensional surface. In this perspective, the universe works like a hologram, where our three-dimensional experience is merely a projection of information stored on a distant boundary. It hints that what we perceive as our reality might be just an illusion, rather than a solid existence. There's also the idea known as quantum cosmology, which incorporates principles from quantum mechanics, the study of the incredibly small particles that make up everything. This theory suggests that the universe may have emerged from a quantum fluctuation in a stable vacuum. Think of it as a tiny bubble popping into existence from nowhere, leading to the birth of space and time as we know it. Each of these theories presents a unique perspective on the origins of our universe, revealing the complexity and mystery that remains in cosmology. Even while the Big Bang theory is widely accepted, science continues to explore and question, always searching for deeper understanding in the vast expanse of existence. Cyclic models of the universe present an intriguing view that challenges the traditional understanding of creation from nothing. In the most common scenario of cosmic origins, we often hear about the Big Bang, a dramatic event that marks the birth of our universe. This model suggests everything emerged from a singular moment in time, where space, matter, and energy sprang into existence. The idea of beginning from nothing feels compelling, but cyclic models introduce a different perspective. In a cyclic universe, cosmic events do not start from absolute nothingness. Instead, the universe undergoes endless cycles of expansion and contraction, much like a heartbeat. After a period of expansion, a contraction phase follows, pulling everything back together. This might create conditions perfect for a new expansion, leading to another Big Bang. This cycle repeats infinitely, where each cycle flows into the next. This notion implies that the universe is eternal in a different sense. There is no singular moment when everything began. Instead, there is a series of rebirths. Time and space are not one-time creations but part of an ongoing process. As a result, rather than arriving from nothing, each cycle is shaped by the remains of the previous one. Thus, cyclic models question the narrative of a one-time origin, suggesting that our universe may be part of a much larger, timeless process of cosmic rebirth. This revision leads to profound implications about the nature of existence and the potential for understanding the universe in a more complex and layered manner. The evolution of the universe is a remarkable journey that begins with a singular, incredibly hot and dense state, often referred to as the Big Bang. This event occurred approximately 13.8 billion years ago, marking the beginning of space, time, and all matter. In that moment, everything we know began expanding rapidly from this tiny point, a process called cosmic inflation. As the universe expanded, it cooled. This cooling allowed the most basic elements to form, primarily hydrogen and helium, along with trace amounts of lithium. Over time, these gases began to clump together due to the force of gravity, forming the first stars and galaxies several 100 million years after the Big Bang. Inside these stars, nuclear fusion ignited, producing heavier elements and light. When these stars eventually died, they exploded in cataclysmic events known as supernovae, scattering these new elements across space. The remnants from these explosions acted as raw materials for the next generation of stars and planets. As millions of years passed, gravity continued to play a vital role in shaping the cosmos. Smaller gas clouds collapsed to become stars, and the stars formed clusters known as galaxies. The interactions among these galaxies further fueled the universe's growth and complexity. Within galaxies, stellar systems like our own solar system began to form. Planets, moons, and other celestial bodies coalesced from dust and gas around young stars. On Earth, chemical processes led to the emergence of life, adding yet another layer to the universe's evolution. Today, we observe a cosmos filled with billions of galaxies, each harboring countless stars and planets, showcasing the intricate tapestry woven over billions of years. The universe continues to evolve even now, expanding at an accelerating rate, as dark energy drives this mysterious force that pushes galaxies apart. Understanding this cosmic history helps us appreciate not just where we came from, but also our place in the vast universe, constantly shaped by the laws of physics and the forces of nature. Cosmic events like supernovae offer profound insights into the origins of the universe and its evolution. A supernova occurs when a massive star runs out of fuel and undergoes a catastrophic explosion. This explosion not only marks the end of the star's life, but also produces an enormous amount of energy and elements that are vital for the formation of new stars, planets, and even life. When we observe a supernova, we are actually witnessing a moment in a star's life cycle that can shed light on how the universe itself has changed over time. These explosions release heavy elements, such as carbon and iron, into space. These materials are essential because they form the building blocks of planets and the basic components of life as we know it. By studying the remnants of supernovae, scientists can trace how these essential elements were distributed throughout the universe, influencing the formation of galaxies and star systems. Furthermore, supernovae can act as cosmic markers. By measuring their brightness and patterns, astronomers can determine distances in the universe. This is crucial for understanding the expansion of the universe itself. For instance, observations of certain types of supernovae have led to the discovery that the universe is not just expanding, but that the rate of this expansion is accelerating. Supernovae serve as both a cosmic blueprint and a clock. They help scientists reconstruct the history of the universe, showing how it has evolved from the chaotic conditions following the Big Bang to the complex structures we observe today. Each explosion adds another chapter to our understanding of how the cosmos came to be and continues to grow and change. Understanding the universe's origin is a monumental task that requires collaboration across various scientific disciplines. Each field brings a unique perspective and set of tools to the table, helping to form a more complete picture of our beginnings. Astronomy is the most obvious player, studying celestial objects and their movements. Through telescopes, astronomers gather light from distant stars and galaxies, allowing them to trace back the history of the universe by observing its expansion. This field helps answer fundamental questions about how cosmic structures formed and evolved. Meanwhile, physicists contribute crucial insights, particularly from the realms of particle physics and astrophysics. They explore the fundamental particles and forces that shaped the early moments of the universe. Experiments conducted in particle accelerators mimic conditions thought to have existed just after the Big Bang, helping scientists understand how matter and energy transformed into the elements we see today. Cosmology, a branch of both physics and astronomy, plays a vital role too. Cosmologists probe the universe's large-scale structure, studying its overall shape, composition, and evolution. They develop theories about cosmic inflation, which suggests rapid expansion occurred shortly after the Big Bang, sculpting the universe into what we observe now. Then we have geology, which complements these efforts by studying planetary bodies, including Earth. Geologists examine the formation of our planet and its materials, offering insights into how life's conditions might have developed. Understanding the Earth's history provides context for the broader narrative of cosmic evolution. Lastly, computer science and data analysis are indispensable in this collaborative effort. Advanced simulations allow researchers to test their theories about the universe's origin. By modeling scenarios based on current knowledge, scientists can visualize events from the very start of time, following the cosmic evolution across millions, even billions of years. Collectively, these diverse scientific disciplines create a mosaic of understanding, with each piece contributing to a greater narrative about our universe's inception. Collaboration between these fields fosters innovative approaches and fuels discoveries, pushing the boundaries of our comprehension further with each finding. Particle physics and cosmology both provide fascinating insights into the concept of nothing. At first glance, nothing seems like an absence, like empty space devoid of matter. However, scientists have discovered that what we often consider empty is anything but. In particle physics, the vacuum is not simply an empty void, rather it is a seething backdrop of virtual particles popping in and out of existence. These particles appear due to the fundamental qualities of quantum mechanics, which allows energy fluctuations even in the absence of matter. So rather than an emptiness, the vacuum teems with potential. Cosmology takes this notion further by examining the universe's inception. The Big Bang theory suggests that the universe began from an extremely hot and dense state. Before the Big Bang, it's hard to apply our usual understanding of nothing. It's not merely a lack of material, but may represent a singularity, where the rules of physics as we know them break down. So in cosmic terms, there might not even be a meaningful concept of before if nothing truly existed then. Together, these fields hint that nothing is a complex environment full of energy and possibility, rather than emptiness. Thus, within the framework of modern physics, nothing can be a source of creation, where particles emerge from a seemingly void backdrop and potentially lead to the formation of the universe itself. This challenges our everyday perceptions and encourages us to rethink the limits of existence and the very fabric of reality. Ancient cosmologies, the ways in which early civilizations understood the universe, have surprisingly laid important groundwork for our modern scientific explorations of the cosmos. These ancient stories and theories reflect humanity's early attempts to make sense of celestial events and the nature of existence itself. From the Babylonian creation myths that depicted the universe as formed from chaotic waters, to the Greek philosophers who deliberated the nature of stars and planets, these narratives offered initial frameworks for understanding the world. For instance, the Greeks contributed significantly with thinkers like Aristotle and Plato, who began to ponder the structure of the universe. They proposed geocentric models, where Earth was at the center, surrounded by celestial bodies in a complex arrangement. While we now know that the Earth revolves around the Sun, the questions raised by these early philosophers about the cosmos laid the foundation for systematic observation and reasoning that would later be paramount in scientific breakthroughs. As cultures evolved, so did their understanding. The ancient Indian cosmology presented a cyclical view of the universe, suggesting that creation and destruction are part of a never-ending cycle. This concept resonates with modern theories involving cosmic expansion and potential Big Crunch scenarios, where the universe may eventually collapse back in on itself. The evolution of these ancient ideas showcases humanity's journey from myth to science. As scientists began to develop telescopes and mathematical frameworks in the Renaissance, ideas from the past were revisited and refined. Notably, the heliocentric model proposed by Copernicus and further substantiated by Galileo's observations directly challenged the geocentric views prevalent since ancient times. Moreover, today's Big Bang theory, which describes the universe's rapid expansion from a singular beginning, echoes ancient creation myths that seek to explain how everything came to be. The agile movement in ancient cosmologies provides a philosophical perspective that is now reflected in scientific inquiries. Thus, while our technology and understanding have advanced immensely, the themes and questions asked by ancient civilizations still resonate in modern scientific thought. They remind us that the quest for knowledge is a continuous thread through human history, one that connects our deepest existential questions with cutting-edge research in astrophysics today. Many mythologies around the world portray the creation of the universe as emerging from a state of nothingness. In these tales, the void is often described as deep silence or utter darkness, a blank canvas from which everything eventually arises. In ancient Greek mythology, the story begins with chaos, a primordial void that existed before anything else. From this emptiness, the first entities emerged, such as Gaia, the Earth, and Eros, representing love and attraction. These beings then shaped the cosmos, giving rise to the universe through their actions and relationships. In Hindu mythology, the concept of creation also starts from a state of nothingness. The cosmic ocean, often described as an endless void, is initially filled with darkness. Out of this void, Brahma, the creator god, awakens. He then creates the universe, all living things, and the intricate balance of existence through a series of powerful acts. The Maori culture from New Zealand describes a similar narrative. In the beginning, there was only Te Po, the darkness. From this deep nothingness, light emerged when the primal parents, Ranginui, the Sky Father, and Papatuanuku, the Earth Mother, were separated, allowing life and the universe to flourish. Even the biblical account offers a perspective on beginnings from nothing. It describes an infinite formless void through which God spoke the universe into existence, calling forth light and forming the earth and sky from what was previously non-existent. These myths may differ in characters and the specifics of their tales, but they all share a common theme: the transformation of nothingness into the vast complexity of the universe we perceive today. Each narrative reflects human curiosity and a desire to understand our origins, showcasing creativity and meaning in the face of the unknown. If the universe truly originated from nothing, it raises profound philosophical questions that challenge our understanding of existence itself. First, let's consider what nothing means. It is often perceived as the absence of anything: no matter, no energy, no time. The idea that something can emerge from nothing defies our common expectations. It forces us to rethink causality, suggesting that the universe does not need a preceding cause or creator to exist. This leads to the contemplation of existence itself. If the universe can arise from nothing, then perhaps everything we consider essential for creation, such as time and space, might not be as fundamental as we think. If these concepts are merely products of the universe, then what does that say about our own existence? Are we simply a chance arrangement of matter, resulting from an event that had no prior form or guidance? Additionally, this perspective challenges traditional views of creation. Many philosophical and religious frameworks posit a deliberate creator or an ordered process leading to our universe. However, if our universe sprang from nothing, it could imply that the universe is inherently chaotic rather than designed. This might evoke feelings of both wonder and anxiety as we grapple with the idea that existence might be random and unstructured. Furthermore, considering that science may provide evidence for this scenario, it provokes a dialogue between science and philosophy. Should we reassess our approach to understanding the universe? Are we simply observers in a vast, indifferent cosmos that came into being without intention? The possibility of the universe coming from nothing encourages a deeper exploration of consciousness, existence, and the nature of reality. It invites us to ponder our place within this grand, seemingly random unfolding of events, and inspires continuous inquiry into the mysteries that lie at the heart of existence itself. The idea of a universe emerging from nothing challenges our conventional understanding of reality in profound ways. Traditionally, when we think about the universe, we consider everything to be formed from pre-existing materials or conditions. However, imagining a universe that comes into existence from an absence of anything prompts us to rethink the very nature of existence itself. If a universe can arise from nothing, it implies that creation doesn't necessarily require a prior state or substance. This raises big questions about the origins of our reality. It suggests that all the laws of physics, gravity, electromagnetism, and more could emerge alongside space and time rather than being imposed upon them. In other words, the universe wouldn't just appear as a pre-packaged entity, it would unfold with its own rules. This concept encourages us to explore ideas about emptiness and potential. What does it mean for something to be truly nothing? Could it be a fertile ground for new realities, bursting with possibilities? Furthermore, if universes can form spontaneously, it opens the door to the idea that there might be multiple universes existing concurrently, each potentially evolving from its own unique nothingness, leading to a vast multiverse filled with varied conditions and principles. Ultimately, a universe from nothing challenges not just our scientific theories, but also our philosophical perspectives on existence. It inspires curiosity about the unknown, inviting us to think beyond our existing frameworks and consider the essence of reality itself. This invites a new dialogue about creation, existence, and the cosmos that extends far beyond traditional boundaries. The idea that the universe could arise from nothing challenges our understanding of existence and creation in profound ways. Traditionally, we think of creation as something that requires a cause or a starting point, but this concept suggests that our universe could begin without any material or pre-existing conditions. Imagine a vast emptiness where not even time or space exists. The question then arises, What does it mean for something to emerge from nothing? This perspective alters how we perceive the beginning of everything. If the universe can come from nothing, it implies that existence might not need a traditional creator or source. It allows us to consider that the universe's existence is just one possibility among many. Such an idea invites a sense of humility and wonder. It indicates that our understanding of reality may be limited, and that the workings of the cosmos could be far more complex than we imagine. Moreover, if the universe can spontaneously emerge, it opens the door to countless questions about what lies outside of our universe and before its creation. It challenges our beliefs about what is real and what underpins existence. This thought can be both unsettling and exhilarating, prompting us to rethink our place in the cosmos and the nature of reality itself. Rather than seeing creation as a linear story, we begin to appreciate existence as a vast, mysterious process full of surprises and possibilities. The significance of a grand unified theory lies in its ambition to bring together our understanding of the fundamental forces that govern the universe. Imagine breaking down the complex workings of nature into simpler, more understandable pieces. Right now, we have four main forces: gravity, electromagnetism, and the strong and weak nuclear forces. Each force operates differently and explains various phenomena, but they remain disconnected in our current theories. A grand unified theory aims to unify these forces into a single framework. This becomes particularly compelling when looking back at the origins of the universe. Shortly after the Big Bang, all these forces were believed to be interconnected. As the universe expanded and cooled, they began to separate and behave as distinct forces. By discovering a grand unified theory, scientists hope to reveal how this separation occurred, offering insights into the conditions that existed at the very beginning of everything. Understanding these connections can also help us answer profound questions. For example, it may clarify why the universe is structured the way it is, how galaxies formed, and what percentage of its contents consists of dark matter and dark energy. These elements seem to fill the universe, but remain poorly understood. A grand unified theory doesn't just seek to tidy up our scientific understanding. It holds the potential to illuminate the core truths about our universe's inception, providing a more cohesive picture of how everything is linked, from the tiniest particles of matter to the vast cosmos itself. This theory represents a crucial step toward a deeper, more unified understanding of nature's fundamental workings. Supersymmetry is a fascinating idea in physics that suggests for every particle we know, there exists a partner particle. This theory arises from attempts to unify the fundamental forces of nature and provides a way to solve some of the mysteries we face in understanding the universe. Now, when we look back at the beginning of the universe, particularly the moment after the Big Bang, conditions were incredibly high energy and chaotic. At this point, it's believed that particles and forces were not distinct, but instead blended together in a state that we can hardly imagine. Supersymmetry offers a possible explanation for how these forces might have worked together in those early moments. The existence of these partner particles could help explain some unresolved issues, such as dark matter and the imbalance between matter and antimatter in the universe. Dark matter, which makes up a significant portion of the universe's mass, has not been directly observed, yet supersymmetric particles could potentially account for it. Moreover, at the moment of the Big Bang, the universe was so hot that if supersymmetry holds true, the interactions of these particles might have led to various outcomes in the first moments of creation. The dynamics involved could provide insights into why we see a predominance of matter rather than equal parts matter and antimatter today. Overall, by exploring supersymmetry, scientists hope to delve deeper into the fundamental structure of the universe and reveal how everything we observe originated from that singular, explosive moment in time. To explore the origins of the universe, scientists are developing several advanced technologies that promise to enhance our understanding significantly. One of the most exciting advancements is the next generation of telescopes, particularly those designed to observe in a broader range of wavelengths, from infrared to radio waves. These telescopes will allow us to peer deeper into space and look further back in time, capturing light from the very first stars and galaxies that formed after the Big Bang. By studying this ancient light, we can gather valuable clues about how the universe began and evolved. Another promising technology involves particle accelerators. These massive machines smash particles together at incredibly high speeds, recreating conditions similar to those just after the universe's formation. By examining the fundamental particles created in these collisions, scientists can gain insights into the forces and interactions that governed the early universe. These experiments could help us understand the building blocks of everything we see today. Simulation technology also plays a critical role. Researchers are creating highly detailed simulations of cosmic events using powerful computers. These simulations can model different scenarios of the early universe, allowing scientists to test their theories against observational data. By comparing simulations with what we observe through telescopes, we can better grasp how galaxies and cosmic structures developed. Moreover, improvements in gravitational wave detection technology are groundbreaking. Gravitational waves are ripples in spacetime caused by violent cosmic events, such as merging black holes or exploding stars. Detecting these waves opens a new way to observe the universe, providing insights that traditional light-based telescopes cannot. They can offer a clearer picture of the early universe's rapid expansions and behaviors. Each of these technologies contributes to a multifaceted approach to understanding our universe's origins. Collectively, they allow us to gather a wealth of information, revealing the universe's history and the fundamental laws that govern it, bringing us closer than ever to deciphering the enigmatic story of our cosmic beginnings. Over the last century, major discoveries have dramatically changed our understanding of how the universe began. In the early 20th century, scientists began to notice that distant galaxies were moving away from us. This observation suggested that the universe is expanding, which was a groundbreaking idea that led to the formulation of the Big Bang theory. Instead of a static universe, we now understand that everything started from a single, extremely hot and dense point and has been expanding ever since. Further insights came from the discovery of cosmic background radiation, a faint glow filling the universe. This radiation is essentially the afterglow of the Big Bang and serves as critical evidence supporting the idea that the universe had a distinct beginning. It tells us that the universe was once so hot that it filled with light, and as it expanded, this light cooled and became the radiation we detect today. Advancements in technology like powerful telescopes and satellites have allowed us to observe ancient light from the early universe. Observing this light provides a glimpse back in time, helping us understand conditions shortly after the Big Bang. Additionally, studies of distant galaxies and cosmic structures have clarified how matter and energy have evolved over billions of years, shaping everything we see today. Discoveries in particle physics have also contributed to our understanding of the universe's origins. They helped reveal the behaviors of fundamental particles that make up everything in existence, including those that formed in the early moments after the Big Bang. This knowledge has illuminated the fundamental forces of nature and how they have shaped the development of the universe. The combination of these discoveries paints a fascinating picture of the universe as a dynamic, evolving entity with a rich history. This knowledge emphasizes not only how we came to be, but also our ongoing relationship with the cosmos, continually revealing new depths of understanding about our origins. Our understanding of the universe's origin is still a work in progress, with several key limitations that scientists are actively exploring. The leading theory, known as the Big Bang theory, suggests that the universe began from an extremely hot and dense state, approximately 13.8 billion years ago. However, there are many aspects of this theory that remain unclear. One significant limitation is the lack of direct evidence from the very first moments after the Big Bang. Our ability to observe and measure phenomena is constrained by the fact that the universe began as a hot, opaque state. Only after a short while did it cool enough for light to travel freely, leading to the cosmic microwave background radiation, which we can detect today. However, this radiation does not provide a complete picture of the events that occurred in the immediate aftermath. Another challenge lies in understanding what came before the Big Bang, or if the concept of before even applies. Current theories struggle with the idea of time and space existing prior to this event. Some propose concepts like cosmic inflation, suggesting that the universe experienced an exponential rapid expansion shortly after the Big Bang, But these ideas are still being tested and refined. Additionally, while the Big Bang theory explains the expansion of the universe, it does not address what caused the initial burst of energy or the fundamental principles guiding that expansion. The existence of dark matter and dark energy, substances that seem to exert a significant influence on the universe's structure and behavior, is another layer of mystery. These elements make up a vast majority of the universe, yet we have limited understanding of their nature and origins. Finally, the role of quantum mechanics in the early universe also poses questions that challenge our current models. The interplay between the vast scales of cosmic events and the tiny scales of quantum physics is not yet fully understood, leading to uncertainties regarding how these two realms interact during the universe's formative moments. While we have made significant strides in understanding the universe's origins, substantial questions remain about the events leading up to and immediately following the Big Bang, the nature of what preceded it, and the fundamental forces influencing the cosmos. Each discovery opens new avenues of inquiry, keeping this field both dynamic and fascinating. When exploring the beginning of the universe, scientists confront numerous unknowns. They take an investigative approach by combining evidence from various fields of study such as astronomy, physics, and cosmology. They begin by examining the cosmic background radiation, which is akin to a faint afterglow from the Big Bang, providing essential clues about the early universe. In addition to gathering data from observations, scientists also rely on theoretical models to hypothesize how the universe may have started. One popular theory is the Big Bang model, which suggests that the universe began from a singular point and expanded rapidly. Researchers run simulations and calculations to see how this model aligns with current observations. Moreover, scientists recognize that there are gaps in what we understand, which leads to the formulation of new questions. They seek to refine existing theories and develop novel ones by challenging assumptions and encouraging fresh ideas. Events that cannot yet be explained, such as the nature of dark matter and dark energy, serve as focal points for ongoing studies. To further investigate these unknowns, large research collaborations, observatories, and particle accelerators are utilized. These facilities allow researchers to study cosmic events and particles that could shed light on the universe's origins. With time, as technology advances and new discoveries emerge, the scientific community continues to piece together the puzzle, embracing uncertainty as part of the journey toward greater understanding. The idea that the universe could emerge from nothing is both fascinating and complex. Currently, scientists propose that before the universe began, there may have been a state devoid of matter and energy. This concept suggests an existence that is fundamentally different from our usual understanding. As we discover more about quantum physics, we learn that even in what we consider nothing, there can be fluctuations of energy. These tiny bursts can give rise to particles and forces. Imagine it as a calm sea, where under the surface, small waves of activity can suddenly rise. This leads to questions about the beginning of the universe. Could the conditions present in this nothing be sufficient to spark the creation of everything we see today? Future discoveries such as the exploration of dark matter and dark energy, two mysterious aspects that seem to shape the universe, could reshape our understanding of how the cosmos began. If we find that these elements play a vital role in the birth of the universe, it might suggest that nothing is not as empty as we once thought. Instead, it might be a dense fabric of potential and chaos waiting for the right conditions to give birth to universes. Additionally, advancements in technology and experiments could lead us to comprehend the forces and rules governing the very early universe. If we can glean more insights into how energy and particles interacted after the initial creation event, our perception of a universe arising from absolute emptiness could shift dramatically. Future discoveries may reveal a universe that is much more interconnected and dynamic, challenging the simple idea of creation from nothing and opening up a deeper appreciation of how complex and breathtaking our cosmos truly is. The theory of cosmic inflation is a fascinating concept that helps explain the early moments of our universe. Imagine a balloon lying flat on a table. Now, when you blow air into it, the balloon expands rapidly. This inflationary stage suggests that, right after the Big Bang, the universe underwent an incredible expansion. growing enormously in size in just a fraction of a second. This rapid growth isn't just about getting larger, it also smooths out the cosmos, leading to a more uniform distribution of matter and energy. Before inflation, the universe was likely very chaotic, with clumps of matter scattered unevenly. As inflation took hold, it stretched this initial chaotic state into a vast, even tapestry. Now, when discussing a universe emerging from nothing, inflation provides a compelling narrative. The idea of nothing doesn't mean absolute emptiness, but rather a state with no particles, no stars, and no matter as we know it. It suggests that the universe could arise from a quantum vacuum state, a kind of energy that exists in a minimal state. This quantum vacuum didn't just remain static. Through a process that we don't fully understand yet, this energy transitioned, triggering the rapid expansion known as inflation. Inflation bridges the gap between a universe that seems to emerge from nothing and the complex cosmos we see today. It helps explain how a tiny, uniform region of space could evolve into the vast universe full of galaxies, stars, and planets after its initial explosive growth. Through this lens, cosmic inflation not only enriches our understanding of the universe's birth, but also invites us to reconsider what we mean by nothing in the grand scheme of existence. The theory of cosmic inflation proposes that the universe underwent a rapid expansion shortly after the Big Bang, growing faster than the speed of light in a very brief period. Several pieces of evidence support this idea. First, one of the main pieces of evidence comes from the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This radiation is uniform across the sky, but tiny variations exist. Inflation theory explains these slight fluctuations as the result of quantum effects during that brief period of rapid expansion. These variations provide clues about the early distribution of matter and energy in the universe. Another supporting factor is the large-scale structure of the universe. If the universe had not gone through inflation, we would expect to see a different arrangement of galaxies and galaxy clusters. Instead, their distribution aligns well with predictions from inflation, showing a pattern that suggests a very homogeneous and isotropic early universe that expanded dramatically. Additionally, the observable universe is nearly flat in terms of geometry, which is consistent with inflation. This flatness hints that the universe expanded and spread out the initial density fluctuations evenly. If inflation occurred, it would naturally lead to a universe where the overall geometry balanced out to a flat shape. Lastly, data gathered by telescopes and observatories, such as measurements of the cosmic microwave background and the distribution of galaxies, have shown results that closely match the predictions made by inflation theory. These observations reinforce the notion that a rapid expansion very early in the universe's history is a compelling explanation for what we see today. Religious creation stories and scientific theories of the universe's beginnings present two fascinating perspectives on the same fundamental question. How did everything all begin? Many religious traditions have their own unique narratives that often explain the universe's origins as the acts of a divine being or beings. These stories usually involve a purposeful creation where a higher power brings forth the world and everything in it. They may emphasize themes of order emerging from chaos and the significance of creation from a spiritual viewpoint. On the other hand, scientific theories seek to understand the universe's beginnings through evidence and observation. One widely accepted scientific view is that the universe began with an event commonly known as the Big Bang. This theory suggests that the universe once existed as a very hot, very dense point that suddenly expanded. In this vast cosmic explosion, matter and energy spread out, forming galaxies, stars, and planets over billions of years. Importantly, discussions about the universe starting from nothing in a scientific context often deal with complex ideas about quantum physics and the nature of time and space. While religious stories tend to provide a narrative that conveys moral and existential meanings to believers, scientific theories aim to present explanations based on empirical evidence. However, both realms are rich with imagination and wonder, offering ways to explore the human experience in relation to the cosmos. In many ways, people often find themselves drawing personal connections between the two, wrestling with the wonder of existence whether through spiritual beliefs or scientific inquiry. Each perspective, whether viewed through faith or skepticism, contributes to our shared quest for understanding the mysteries of the universe. Religious interpretations can play a significant role in shaping how people understand the universe's origins. Many religious traditions provide narratives about creation that often involve a divine force or being. These narratives offer followers a framework for understanding their place in the universe and how everything came to be. As a result, individuals influenced by these teachings might prioritize theological explanations over scientific ones when contemplating questions about the universe's beginnings. On the other hand, science approaches the question of origin through observation, experimentation, and empirical evidence. Theories such as the Big Bang provide a scientific narrative that describes the universe's creation based on cosmic background radiation and the expansion of galaxies. For many, these scientific insights can coexist with religious beliefs, creating a blend where one does not necessarily negate the other. Some view science as a way to understand the mechanisms of creation described in religious texts. However, tension can arise, particularly when specific scientific findings seem to contradict literal interpretations of religious texts. For example, if a science-based perspective suggests that the universe is billions of years old, it might clash with a belief in a young Earth, as described in some religious doctrines. In such cases, individuals and communities may engage in reinterpretation of sacred texts or embrace alternative views that reconcile their faith with scientific understanding. Ultimately, the interplay between religion and science regarding the universe's origin is complex. Individuals navigate this landscape in various ways, often influenced by cultural backgrounds, personal beliefs, and the interpretations available in their religious communities. This interaction showcases how deeply held beliefs can mold perspectives on profound questions about existence, creation, and the cosmos itself. Discoveries in particle physics act like a magnifying glass for the early moments of the universe. To comprehend how everything began, scientists study the smallest building blocks of matter, known as particles. These particles are the foundational elements that come together to form atoms, which eventually create everything we see around us. In the very beginning, right after the Big Bang, the universe was a hot and dense soup of particles all colliding and interacting. As the universe expanded and cooled over time, these particles began to assemble into atoms, leading to the formation of stars, galaxies, and eventually planets. Particle physics helps us understand the forces involved in this process, like gravity and electromagnetism, which govern how particles behave. One significant discovery comes from studying particles known as bosons, which include the famous Higgs boson. This particle explains how other particles get their mass, which is crucial for the existence of matter as we know it. Without mass, particles would zip around at the speed of light, unable to form the structures that make up the universe. Furthermore, collisions in particle accelerators create conditions similar to those just after the Big Bang. These experiments allow scientists to observe how energy transforms into various particles. Each new discovery adds pieces to the puzzle, helping to paint a clearer picture of how the universe evolved from a chaotic burst of energy to the organized cosmos we inhabit today. Thus, the insights gained from particle physics are not just focused on the tiniest elements, but reach far into understanding the grand story of the universe's origin. They help answer profound questions about why the universe has the structure it does and what laws govern it, offering clues about the very nature of existence itself. Particle accelerators are powerful tools that help scientists explore the fundamental building blocks of matter, and their role in simulating early universe conditions is both fascinating and essential. Imagine the very beginning of the universe, an incredibly hot and dense state bursting forth into expansion. To understand that moment, researchers recreate similar extreme conditions right here on Earth. When particles such as protons are accelerated to extremely high speeds and smashed together, they generate immense energy. This energy can transform into various particles, mimicking the processes that occurred when the universe was just beginning to cool and evolve. During these high-energy collisions, conditions like those found in the early universe are briefly recreated, allowing scientists to study the behavior of fundamental particles and the forces that govern them. These experiments can produce exotic particles that are fleeting, much like what may have existed in the moments after the Big Bang. By observing these particles, scientists can gain insight into the basic forces, like electromagnetism and the strong force that shaped the formation of matter. They can also explore phenomena such as quark-gluon plasma, an extremely hot state of matter thought to have existed just after the Big Bang. Particle accelerators work like time machines, helping us peek into the universe's infancy. Through this investigation, researchers can piece together the puzzle of how everything we see around us today originated from those first moments of the universe. Each collision, each new particle observed, takes us a step closer to understanding our cosmic history. While the Big Bang theory provides a widely accepted explanation for the universe's beginning, scientists are continually exploring new ideas to understand our cosmos better. One intriguing model is the steady-state theory, which suggests that while the universe is expanding, it also creates new matter to fill the gaps. This idea implies a universe that has no beginning or end, providing a consistent appearance over time. Another captivating concept is the cyclical universe model. In this framework, the universe undergoes endless cycles of expansion and contraction. Imagine a balloon being inflated and then deflated repeatedly. It reflects a universe that expands to a great size and then collapses back into a singular point, only to start anew. This model challenges our conventional view of time as linear. The multiverse theory presents yet another possibility. It posits that our universe might be one of many, each with its own set of physical laws and constants. Think of it as a vast ocean of bubbles, where each bubble represents a different universe, including variations in time and space. This concept raises fascinating questions about existence itself and the potential for different realities coexisting simultaneously. Additionally, there are string theory and quantum gravity models, which aim to merge the principles of quantum mechanics with general relativity. These theories suggest complex structures at the atomic level that could influence the overall makeup and history of the universe. While still largely theoretical, they invite us to rethink our understanding of the fundamental forces that shape everything we see. Each of these models adds a different layer to our comprehension of how the universe might have begun and continues to evolve, demonstrating that the quest for knowledge is ever expanding. The exploration of these ideas not only deepens our understanding, but also sparks new questions about the infinite possibilities of existence. Conformal cyclic cosmology presents a fascinating perspective that contrasts with traditional Big Bang theories. In the standard view, the Big Bang is seen as a single, explosive event marking the beginning of our universe, leading to a gradual expansion over billions of years. This theory suggests that the universe will eventually reach a death phase, when stars burn out and galaxies drift apart until everything is cold and dark. In contrast, conformal cyclic cosmology proposes that the universe undergoes a series of infinite cycles. Each cycle begins with a Big Bang, but crucially, it extends the notion of time and space in a unique way. As the universe expands and ages, it eventually reaches a state of smoothness where time and space become less distinct. In this model, the end of one universe seamlessly transitions into the beginning of the next. The key innovation of this theory is its use of conformality, which means that the details of the universe's structure can become less relevant as it ages. In other words, the universe forgets its previous state after each cycle, allowing the next Big Bang to start over without remembering the past. This is like a well-worn book that, over time, becomes a blank page, ready for new stories to be written. The primary difference lies in the concept of time. While traditional Big Bang theories adhere to a linear progression of time leading to an ultimate fate, conformal cyclic cosmology envisions an ongoing, repeating series of developments. In this way, it challenges our understanding of the universe's life cycle, inviting us to rethink the nature of beginnings and endings in a cosmic context. Each cycle could contain its own history, suggesting that the universe is not a one-time anomaly, but rather an eternal sequence of rebirths. Observational cosmology is like a giant window into the past of our universe. By studying light and other signals from distant galaxies, stars, and cosmic phenomena, scientists can piece together a timeline that reveals how everything began. One key aspect of this field is observing the cosmic microwave background radiation. This faint glow fills the universe and is a remnant from an early time when the cosmos was still hot and dense, shortly after the Big Bang. By examining this radiation, researchers can uncover details about the conditions of the universe almost immediately after its formation. Another important discovery comes from observing how galaxies are moving. Many galaxies appear to be drifting away from us, and this observation leads to the understanding that the universe is expanding. This expansion suggests there was once a moment when everything was concentrated in a very small point, often referred to as the singularity, marking the beginning of the universe. The rate at which galaxies are moving apart helps scientists estimate how long ago this expansion started. Additionally, by studying the distribution and behavior of different cosmic structures, such as galaxies and clusters of galaxies, researchers can develop models that explain how they came together over billions of years. These models not only tell us about the forces at play, but also hint at the kinds of substances, like dark matter and dark energy, that govern the universe's evolution. Each new observation serves as a piece of a vast puzzle. As telescopes and technology improve, they allow for even deeper explorations of the universe. This is leading to richer insights about the origins of everything we see, prompting new questions about the nature of time, space, and the very fabric of reality itself. Observational cosmology is continuously reshaping our understanding of how the universe began and where it may ultimately lead. The Hubble Space Telescope has unlocked many mysteries about the universe's origin, offering crucial insights that have shaped our understanding. One of its most significant findings is the measurement of the rate at which the universe is expanding. This expansion was first suggested by observing that distant galaxies are moving away from us, indicating that the universe itself is stretching out like an inflating balloon. Hubble helped refine the value of this expansion rate, leading to a better understanding of how the universe has evolved over time. Hubble has also captured stunning images of distant galaxies, helping astronomers investigate their formation. By looking deeper into space, Hubble essentially looks back in time because light from those distant galaxies takes millions and sometimes billions of years to reach us. This has allowed scientists to study galaxies as they were when the universe was much younger, revealing how they formed and changed over time. Another remarkable discovery from Hubble involves the cosmic background radiation. This faint glow, permeating all of space, is a remnant from the early universe, and its properties suggest that the universe began with a hot, dense state. By measuring variations in this radiation, Hubble contributed to a more accurate age estimate for the universe, showing that it is roughly 13.5 billion years old. Additionally, Hubble has played a crucial role in identifying dark energy, the mysterious force driving the acceleration of the universe's expansion. By studying supernovae and their brightness, Hubble helped uncover surprising evidence that shows the rate of expansion is increasing, offering a clue to the universe's fate. The Hubble Space Telescope has provided invaluable evidence about how the universe began, its expansion, the formation of galaxies, the nature of cosmic background radiation, and the role of dark energy, enriching our comprehension of the cosmos and its evolution throughout time. Theories about the universe's origin address time in fascinating ways. To start, one of the most prominent ideas is the Big Bang theory, which suggests that the universe began as an incredibly small and hot point. At the moment of this initial explosion, everything we know, including space and time, came into existence. Prior to the Big Bang, the concept of time as we understand it may not have even existed. As the universe expanded from that initial moment, time began to unfold like a freshly opened flower. This means that time is not a constant force already present, but an essential part of the universe itself, intertwined with matter and energy. The passing of time marks changes in the universe, like the formation of stars and galaxies, which help us measure and understand this flow. Scientists further explore how gravity can also affect time. The stronger the gravitational field, the slower time flows, which means that in regions near massive objects like stars or black holes, time can stretch and bend. This relationship between time and space has led to fascinating implications about how we understand the evolution of the cosmos. Overall, these theories illustrate that time is not a separate entity, but rather a fundamental aspect that emerged with the universe itself, continually evolving alongside everything within it. Time plays a crucial role in differentiating between the concept of nothing and the universe as we know it. Imagine nothing as a state where existence does not apply. There's no movement, no change, and no events taking place. In this void, time itself would have no meaning because there is nothing to mark its passage. It would be a complete absence of reality. In contrast, the universe is constantly in flux. It is filled with phenomena, stars forming, galaxies colliding, and life evolving. These processes exist within the framework of time, which allows us to measure and experience change. Without time, we could not understand concepts like cause and effect. Every action or event requires a timeline to unfold. When we think about how the universe began, for instance, time emerged from the very first moments after its birth, often referred to as the Big Bang. In this event, time and space began at once, creating the conditions necessary for everything we see. Quantum cosmology explores the origins of the universe by examining the smallest units of reality and how they connect to the cosmos. Imagine the concept of nothing as a state without matter or energy, a blank canvas devoid of any physical presence. Yet, in the fabric of quantum mechanics, this nothingness is not truly empty. It is filled with possibilities, like a bubbling pot that could suddenly give rise to new ingredients. In this realm, particles can appear and disappear in short bursts, a phenomenon known as quantum fluctuations. This idea suggests that, under certain conditions, nothing can transform into something. Quantum cosmologists propose that at the very beginning, our universe might have emerged from such fluctuations, where energy and particles popped into existence from a void. To visualize this, consider a calm surface of water. If you throw a pebble, ripples spread out, creating waves that are visible. Similarly, the birth of the universe may have been initiated by a small, energetic fluctuation that expanded rapidly, leading to the formation of galaxies, stars, and all the complexity we see today. This framework also implies that time itself began with the universe's emergence. Therefore, asking what happened before the universe does not apply, since time as we know it started with its creation. Quantum cosmology not only sheds light on the universe's origin, but also challenges our understanding of reality. It invites us to rethink concepts of existence and the fabric of the universe itself, revealing a dynamic interplay between chaos and order, even at the most foundational level of nature. The Wheeler-DeWitt equation is a fundamental concept in the field of quantum cosmology, where it acts as a bridge between general relativity and quantum mechanics. To grasp its significance, imagine trying to describe the universe's entire history and structure not in terms of time, but through a snapshot of its geometry. This equation captures the idea that the universe does not evolve in the traditional sense, as it does in everyday experiences. Instead, it exists in a timeless framework. At its core, the Wheeler-DeWitt equation represents the wave function of the universe, a mathematical description of all possible states of the cosmos. In quantum mechanics, systems typically change over time, but in the realm of cosmology, the equation reflects a state where all possibilities coexist simultaneously. This perspective allows scientists to explore fundamental questions about the universe's origins, such as what conditions led to the Big Bang and how gravity interacts with quantum effects. The equation itself is rooted in the principles of quantum mechanics while also incorporating aspects of general relativity. In doing so, it suggests that the universe's fabric is intertwined with quantum fluctuations. These fluctuations can lead to the creation of various structures like galaxies and stars from the chaotic background of the early universe. However, working with the Wheeler-DeWitt equation poses significant challenges. The lack of a clear notion of time within the equation makes it difficult to derive classical events from quantum origins. Researchers continue to explore its implications and seek ways to extract meaningful predictions about the universe. By delving into this profound equation, scientists aim to unlock deeper insights into the very nature of existence itself. Recent discoveries in astronomy and physics have significantly reshaped our understanding of how the universe began. For a long time, many believed that the universe started from a static state, but this idea has evolved dramatically with new evidence. One of the most pivotal concepts is the Big Bang theory, which suggests that the universe began as a tiny, hot, and dense point before expanding rapidly. Observations from powerful telescopes reveal the afterglow of this event, known as cosmic microwave background radiation. Imagine a universe that was once a glowing ball of energy. As it expanded, this energy cooled and spread out, giving rise to the radiation we can still detect today. This discovery supports the idea that the universe is not just vast, but dynamic and ever-changing. Furthermore, recent advancements in understanding dark energy have presented another layer to the story. Dark energy is an invisible force that seems to be driving the accelerated expansion of the universe. This means our universe is not only expanding, but doing so at a faster pace than before. This has prompted scientists to rethink the fate of the universe, raising questions about its long-term behavior and ultimate destiny. Additionally, the discovery of exoplanets, planets outside our solar system, has expanded our perspective on the conditions that might exist in the universe. The search for potentially habitable worlds and signs of life has led to the exciting possibility that the processes that governed our universe's early moments might also be occurring elsewhere. Together, these discoveries provide a richer, more complex picture of our universe's beginnings and evolution. Each finding adds a new layer of understanding, suggesting the universe is a dynamic entity, full of surprises and mysteries waiting to be explored. Scientists are constantly developing innovative techniques to unlock the secrets of the universe's beginnings. One of the most exciting methods involves the use of advanced telescopes and observational technology. These instruments are designed to capture light and other forms of radiation emitted by the earliest galaxies and cosmic structures. By examining this light, researchers can gather clues about the conditions that existed just after the Big Bang, which occurred around 14 billion years ago. Another promising technique is the analysis of cosmic microwave background radiation. This faint glow fills the universe and is the remnant heat from the Big Bang. By studying this radiation through sophisticated detectors, scientists can learn about the universe's expansion and the density of matter over time, providing critical insights into its early stages. Gravitational waves, ripples in space-time caused by massive cosmic events, are also becoming a vital tool. By detecting these waves, scientists can observe phenomena that happened in the very early universe, offering a different perspective on its origins than traditional light-based methods. This approach allows a glimpse into the cataclysmic events, like merging black holes and neutron stars, that have shaped our cosmos. Additionally, simulations on powerful supercomputers enable researchers to recreate the conditions of the early universe. By modeling cosmic evolution, they can predict how structures formed and evolved, helping to validate or challenge existing theories. When combined with actual observational data, these simulations provide a more detailed understanding of how the universe transitioned from a hot, dense state to the vast, complex cosmos we see today. Together, these developing techniques enhance our ability to study the universe's origins, breaking new ground in our quest to understand where we came from and how it all began. Each new discovery adds a piece to the cosmic puzzle, revealing the incredible story of our universe's early moments. A universe born from nothing challenges our understanding of existence itself. Imagine a state where there is no matter, no space, and no time. In this scenario, the universe might emerge from a quantum fluctuation. Instead of a traditional beginning, it would represent a spontaneous event where energy forms and then evolves into matter, leading to the creation of a vast cosmos. The characteristics of such a universe would likely include a chaotic and rapid expansion. Initially, this universe could be incredibly hot and dense, unsuitable for any form of life or structure as we know it. But as it expands, it cools, allowing matter to form into simple particles. In time, these particles could come together, driven by gravitational forces, eventually creating stars, galaxies, and further complexities. Another intriguing aspect of this universe is that it may lack any initial conditions that we typically associate with our universe, such as specific laws of physics. Instead, its properties could develop over time, influenced by the interactions of particles and fields. This could mean that the laws governing it might differ significantly from what we experience, leading to unexpected phenomena. In this creation story of a universe from nothing, the concept of time would also emerge. Initially, moments may be indistinguishable, but as structures form and evolve, time would begin to pass as we recognize it, a measure of change in an ever-expanding tapestry of reality. Ultimately, this universe could be similar to our own in some respects, but would have its unique set of rules and characteristics born from the sheer possibility of existence arising from absolute nothingness. To understand how scientists predict conditions in a universe that may have originated from nothing, we first need to clarify what nothing means in this context. In scientific discussions, nothing often refers not to an absolute void, but to a state devoid of traditional matter and energy. This concept is a complex idea that challenges our everyday perceptions. Scientists use theories from physics and cosmology to explore how the universe emerged from such a state. One prevalent idea is that the universe began with a massive expansion, often called the Big Bang. Before this event, there might have been energetic fluctuations even in that so-called nothing. These fluctuations could have led to the creation of particles and the subsequent formation of energy, which eventually birthed the universe we know today. To predict conditions in this universe, scientists rely on three key elements: theoretical models, observational evidence, and mathematical frameworks. Theoretical models attempt to lay out scenarios of how particle interactions and energies can lead to the formation of the universe. For example, quantum physics suggests that particles can spontaneously appear due to fluctuations in energy fields. Observational evidence, gathered from telescopes and particles colliding in advanced laboratories, feeds into these models. The cosmic microwave background radiation, a remnant of the early universe, provides crucial clues about its origins and conditions shortly after the Big Bang. By analyzing this radiation, scientists can understand temperature fluctuations and density variations that occurred in an incredibly hot and dense early universe. Mathematics plays a vital role as well. Physicists use complex equations to describe how time, space, and energy interact. These equations help in constructing predictions about the universe's evolution, even from a seemingly empty beginning. When they input various parameters, they can produce simulations that show how galaxies, stars, and other structures might form over billions of years. Ultimately, while the idea of a universe arising from nothing sounds paradoxical, scientists use a blend of theoretical exploration, empirical data, and mathematical interpretations to predict how our vast cosmos came into existence and evolved. This ongoing research continuously reshapes our understanding of the universe's beginnings and the complex nature of reality itself. Visualizing nothing is a fascinating challenge that engages both scientists and artists, though they approach it from different perspectives. For scientists, nothing often refers to the concept of a vacuum, a space devoid of matter. In the universe, such areas can exist where there are no particles or atoms, yet they are not completely empty. Even in these voids, there are fluctuations of energy and fields that can influence phenomena. Scientists use sophisticated models and simulations to represent these areas, visualizing how energy behaves in what seems to be an empty space, helping us understand the fundamental nature of the universe. On the other hand, artists tackle the idea of nothing through different mediums like painting, sculpture, or digital media. They might create vast empty spaces or use minimalistic designs to evoke the feeling of absence. For instance, an artist may paint a large canvas in a single color, invoking a sense of emptiness and allowing viewers to reflect on what nothing means to them personally. This creative expression opens up conversations about silence, void, and absence, encouraging people to ponder what exists in that emptiness. Together, both scientists and artists explore nothing by merging factual interpretations and emotional impressions. While scientists provide the underlying theories that describe a lack of matter, artists offer a space for introspection on what that lack means to humanity. This collaboration enriches our understanding of concepts that are inherently difficult to perceive, making the abstract notion of nothing more tangible in our minds. Many people think of nothing as an empty space, a void where absolutely nothing exists. However, in the context of the universe, this idea is not entirely accurate. The concept of nothing can be quite complex. For instance, even in vast empty areas of space, there is still a presence of radiation, particles, and even gravity. Scientists often refer to these as fluctuations in what is called quantum vacuum. which means that even when something seems empty, it is actually teeming with activity at a very small scale. Another misconception is that nothing can exist as a complete vacuum, devoid of any forces or energy. In reality, the universe is filled with dark energy and dark matter, which we cannot directly see but significantly influence the cosmos. These elements are vital to our understanding of how the universe expands, contributing to a kind of invisible substance that shapes its structure. Moreover, some might think that if we could create a true state of nothing, it would be free of time and space. In physics, time and space are interconnected. Removing one also affects the other. Thus, it is impossible to envision a complete nothingness that does not exist within some framework of time and space. This intertwining means that even the most seemingly empty regions of the universe still embody time, albeit in fluctuating, often elusive ways. Lastly, there's a common idea that the universe started from nothing, leading people to simplify the beginning of it all. In scientific terms, the universe originated from a state that was extremely dense and hot, not necessarily from a complete lack of existence. This origin is key in explaining how our universe evolved, transforming into the vast, structured space we see today. Through understanding these misconceptions, we can better appreciate the intricate nature of reality and the cosmos that surrounds us. Understanding the universe's origins is crucial for humanity for many reasons. First, it helps us answer fundamental questions about our existence. By studying how the universe began, we seek to understand not only where we came from, but also our place in the vast cosmos. This knowledge can foster a sense of connection and shared purpose among people, as we realize we are all part of something much larger than ourselves. Additionally, exploring the origins of the universe opens doors to scientific advancements. It propels advancements in technology and methods of inquiry. For instance, creating tools to observe distant galaxies or detect ancient cosmic radiation leads to breakthroughs that can benefit various fields, from electronics to medicine. Moreover, understanding the universe's beginnings enhances our grasp of natural laws. This knowledge can inform our understanding of physics and chemistry, which are essential for innovations in everyday life. It can also prepare us for facing future cosmic events, such as asteroid impacts or changes in the sun's behavior that could affect life on Earth. In a broader sense, unraveling the mysteries of our cosmos encourages curiosity and promotes a scientific mindset. It inspires future generations to engage with science, leading to a society that values education and critical thinking. As we unlock the secrets of the universe, we also confront profound philosophical questions, challenging our beliefs and sparking new discussions about the nature of reality. Ultimately, grasping the universe's origins is not just about knowledge for its own sake. It enriches our understanding of existence, drives innovation, and enhances our ability to navigate an ever-evolving world. Through this quest for knowledge, humanity can foster a deeper appreciation for the universe and our shared responsibilities within it. The quest to understand the universe's beginning has sparked remarkable innovations across many fields of science and technology. At the core of this journey is the Big Bang theory, which posits that the universe began from a singular, hot, dense point and has been expanding ever since. This fundamental idea has prompted scientists to develop new tools and techniques to explore the cosmos. One of the major advancements has been in the field of telescopes. Observatories equipped with powerful instruments allow astronomers to gather light from distant stars and galaxies, revealing their age and composition. Innovations in optics and sensor technology have enhanced our ability to see further into space and back in time, closer to the moment of the Big Bang. Understanding the early universe also requires precise measurements of cosmic background radiation, the afterglow of the Big Bang, that fills our universe. The development of satellites and sophisticated detectors has allowed scientists to study this subtle radiation in detail. Such technologies not only improve our grasp of the universe's infancy, but also lead to advancements in telecommunications and data processing that benefit everyday life. Moreover, the quest to map the universe's expansion has driven innovations in mathematics and computer technology. Complex algorithms help analyze enormous amounts of data from various sources, leading to a better understanding of cosmic structures and dynamics. These algorithms and computational techniques find applications beyond astronomy, influencing data analysis in fields like medicine and finance. Particles that emerged from the Big Bang are studied using high-energy particle colliders. These massive machines, built to smash particles together, probe the very fabric of matter and the forces governing the universe. The technologies developed for these experiments have led to improvements in fields such as imaging and materials science, bringing new solutions to complex engineering challenges. The pursuit of knowledge about the universe's beginning not only deepens our understanding of existence, but also acts as a catalyst for scientific and technological progress. Each question leads to new discoveries, prompting innovation that often has unforeseen applications, ultimately enriching our lives while illuminating the wonders of the cosmos. The beginning of the universe and the formation of black holes are fascinating cosmic events, but they represent very different processes in the timeline of the cosmos. The universe is believed to have started with a great explosion, often called the Big Bang. This event marked the birth of everything we know. Space, time, matter, and energy all originated from an extremely hot and dense point. Imagine a balloon being inflated. As it expands, it allows space itself to stretch and grow, allowing galaxies to move away from each other over vast distances. In contrast, black holes are the remnants of massive stars that have undergone a catastrophic collapse. When such a star exhausts its nuclear fuel, it can no longer support its own weight. Picture a massive building suddenly losing its supports and caving in under its own mass. This collapse creates a concentrated area of gravitational pull so strong that not even light can escape from it, hence the name black hole. While the beginning of the universe represents the opening chapter of everything, black holes are more like enigmatic epilogues, illustrating the life cycles of stars. Where the Big Bang created the conditions for galaxies to form, black holes can play a role in dictating how galaxies evolve later. In certain cases, they may even merge and emit waves through space-time, contributing to the cosmic tapestry of interactions. Both phenomena share the theme of transformation, one unfolding at the universe's inception and the other revealing the life cycle of stars. By studying both, scientists gain insight into the fundamental workings of the universe, from its explosive beginnings to the dark mysteries lurking in its shadows. Each holds clues about the nature of reality and the forces that shape it, resulting in a narrative that is as captivating as it is profound. When we study the death of stars, we gather crucial insights about the entire universe, including its beginnings. Stars are remarkable cosmic engines that forge elements through the process of fusion. As a star exhausts its nuclear fuel, it reaches a point where it can no longer counterbalance the immense force of gravity. This leads to spectacular events, such as supernovae, where a star dramatically explodes, scattering its elements into space. These exploding stars enrich the cosmos with heavy elements like carbon and iron that become the building blocks for planets and potentially life. By examining these phenomena, scientists understand how the basic elements that make up everything, including us, were formed in stars and spread throughout the universe. Moreover, studying the life cycle of stars provides a window into the processes that shaped the early universe. The elements formed in stars contribute to the next generation of stars and galaxies, revealing a continuous cycle of creation and destruction. This cycle helps astronomers piece together a timeline of the universe, from the Big Bang, where only the lightest elements existed, to the rich tapestry of stars and galaxies we observe today. Every time we witness the death of a star, we are catching a glimpse of both the universe's past and its future. Each stellar end marks a critical moment that contributes to the ongoing evolution of the cosmos, allowing us to better understand how it all began. By examining these stellar phenomena, we not only learn about the journey of individual stars, but also about the grand narrative of the universe itself. Symmetry is a fundamental concept that helps scientists understand the universe's origins. At its core, symmetry means that certain properties in nature remain unchanged, even when viewed from different perspectives or conditions. Imagine a perfectly balanced scale. It looks the same and behaves consistently regardless of how you turn it. In the context of the universe, researchers believe that early moments after the Big Bang, the universe was highly symmetrical. This symmetry meant that physical laws were uniform across space and time. Initially, energy and matter might have been evenly distributed, with no preferred direction or form. This state of balance is crucial because it allowed for the emergence of the forces and particles that make up everything around us. As the universe expanded and cooled, this symmetry began to break down. This breaking of symmetry led to the formation of distinct particles like protons and neutrons, and the different forces like gravity and electromagnetism. This transition is similar to how a flowing river can appear seamless, but as it moves, it encounters obstacles that create whirlpools and ripples, giving it structure and variety. By studying these asymmetries and transformations, scientists gain insights into the conditions that prevailed when the universe began. They also explore how the early universe's state influenced the formation of galaxies, stars, and ultimately life. The intricate dance between symmetry and its breaking holds the key to many cosmic mysteries, helping us piece together the story of how everything came to be. This relationship between symmetry and the universe's development is not only fascinating but vital for our understanding of physics and cosmology. Asymmetry in the universe's development from nothing plays a crucial role in shaping the cosmos we observe today. Imagine the universe starting as a uniform field of energy where particles and their counterparts should have formed in equal amounts. However, what we see around us, a universe filled with stars, planets, and galaxies, suggests something went awry. In the early moments after the Big Bang, certain processes allowed matter to dominate over antimatter, despite both being produced in nearly equal amounts. This slight imbalance or asymmetry between matter and antimatter is significant because when matter and antimatter meet, they annihilate each other. If they had been perfectly balanced, our universe would have largely been annihilated, leaving behind nothing but empty space filled with radiation. This asymmetry leads to the existence of the physical world around us. Without it, we wouldn't have stars lighting up the night sky or planets harboring life. Scientists are still working to understand exactly how this imbalance emerged, looking into various theories involving fundamental forces, particle interactions, and even possible new particles. This exploration not only sheds light on the universe's origins, but also on its ultimate fate. Thus, the significance of asymmetry is not merely a detail of the universe's birth, it is a foundational element that allowed the rich complexity of matter to emerge, leading us to our current existence within a vibrant and diverse universe. Quantum entanglement is a fascinating phenomenon where two particles become interconnected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This strange relationship suggests that what happens to one particle can instantaneously affect another, creating a kind of connection that transcends our usual understanding of space and time. When considering the origins of the universe, particularly during the moment after the Big Bang, the concept of quantum entanglement becomes particularly intriguing. In those first moments, the universe was incredibly small and dense, and all particles were likely in a state of intricate, entangled relationships. That means changes or actions at one point could have immediate effects elsewhere in this nascent cosmos. As the universe expanded, these entangled particles would have spread out over vast distances. Despite that separation, their link persisted, suggesting a form of coordination at a fundamental level. This interconnectedness might have helped shape the very fabric of reality, influencing how particles formed into atoms, stars, and eventually galaxies. Moreover, some scientists speculate that understanding quantum entanglement could illuminate how different regions of our universe, which seem far removed from each other in space, may still exhibit correlations. Essentially, the universe's beginnings may have been marked by an intricate web of connections established through quantum entanglement, influencing its evolution in ways we are only just beginning to comprehend. This incredible interplay between particles is a fundamental part of our universe's story, suggesting that even the largest cosmic structures may be rooted in these invisible connections established at the very start of everything. Quantum information theory is an exciting field that explores how information is stored, processed, and transmitted at the smallest scales, where the rules of quantum mechanics come into play. When we think about the origin of the universe, this theory provides unique insights that could change our understanding of how everything began. At its core, quantum information theory suggests that information, much like matter and energy, is a fundamental part of the universe. Imagine the universe as a vast tapestry, with every thread representing a piece of information. In the earliest moments after the Big Bang, the universe was a hot, dense soup of particles and radiation. It is believed that even then, information was being exchanged in ways that we now study through quantum physics. One of the key principles of quantum information theory is entanglement. This phenomenon occurs when particles become linked in such a way that the state of one instantly affects the state of another, no matter how distant they are. This suggests that, at a fundamental level, the fabric of the universe may be interconnected. Some scientists propose that this entanglement might have played a critical role in the conditions right after the Big Bang, helping to establish the early structure of the cosmos. Moreover, quantum information theory introduces the idea that information can be thought of as a valuable resource, akin to energy. As the universe expands, the way information spreads and changes may reveal secrets about its early state and how it developed over time. By examining how information behaves in extreme conditions, researchers may uncover clues about dark matter, dark energy, and other mysterious components that influence the universe's evolution. As scientists delve deeper into quantum mechanics and its relationship with information, they may unlock new understandings of not only how the universe began, but also how it continually reshapes itself. These insights could transform our view of existence itself, blending the realms of physics, information, and the very nature of reality. Several exciting missions are on the horizon, designed to unravel the mysteries surrounding the origins of the universe. One of the most anticipated missions is the James Webb Space Telescope, set to observe distant galaxies and the formation of stars and planets in unprecedented detail. Its infrared capabilities will allow scientists to look further back in time than ever before, revealing insights into the early moments after the Big Bang. Another significant endeavor is the European Space Agency's Euclid mission. This satellite will focus on mapping the geometry of the dark universe by studying the distribution of dark matter and dark energy. By observing large-scale structures in the universe, Euclid aims to shed light on how the universe has evolved over billions of years. Further down the line, NASA's pioneering exoplanet missions also seek to explore the atmospheres of distant worlds. This may indirectly tell us about the chemical ingredients present in the early universe, and how they contributed to the formation of planets that could harbor life. Additionally, ground-based projects like the Large Synoptic Survey Telescope plan to create a detailed map of the cosmos, which will enhance our understanding of the early universe. By capturing massive amounts of data from the sky, these observations will contribute to comprehending how galaxies formed and evolved. These missions not only aim to deepen our understanding of cosmic beginnings, but also inspire new generations of scientists and enthusiasts, igniting curiosity about our universe and our place within it. Each of these projects helps to piece together the intricate puzzle of how everything began, offering glimpses into the vast history of existence. International collaborations in space research bring together diverse expertise, resources, and perspectives, creating a powerful engine for uncovering the mysteries of the universe's origins. By pooling knowledge from scientists around the world, these partnerships enable rigorous exploration of complex questions that no single country might tackle alone. One of the fundamental ways these collaborations advance our understanding is through shared access to cutting-edge technologies and facilities. Each nation may have unique capabilities, such as advanced telescopes, laboratories, or spacecraft. By combining these tools, researchers can conduct broader and more thorough investigations than they could independently. Moreover, international efforts often facilitate large-scale projects, like space missions to study cosmic phenomena or experiments to replicate conditions similar to those just after the Big Bang. For instance, the collaboration of different countries in building powerful observatories helps create a multitude of observations across various wavelengths. This holistic approach leads to richer data and enhances the chances of discovering patterns or anomalies that might hint at deeper truths about our universe. Cultural exchange also plays a pivotal role. As scientists from different backgrounds collaborate, they bring distinct methodologies and viewpoints. This diversity in problem-solving encourages innovative thinking and may lead to breakthroughs that might not arise in a more homogeneous environment. Finally, international collaborations promote a sense of unity in a shared quest for knowledge. By working together, nations collectively confront the unknown and contribute to a legacy that benefits all of humanity. The cooperative spirit that comes from exploring the cosmos can lead not only to significant insights about the universe's beginnings, but also to a stronger global community focused on knowledge and discovery. Artificial intelligence and machine learning are set to become essential tools in unraveling the mysteries of the universe's beginning. Think of these technologies as advanced assistants that can process vast amounts of data much faster than a human ever could. Every time scientists gather new information, whether from space telescopes or particle accelerators, the sheer volume is often overwhelming. AI can sift through this maze of data to find patterns and insights that humans might miss. For example, researchers studying the cosmic microwave background, which is the leftover radiation from the Big Bang, require intricate analysis to identify subtle variations. Machine learning algorithms can be designed to detect these slight differences, revealing secrets about how the universe expanded and evolved over billions of years. By training these systems on existing models and data, they become adept at predicting what new data might reveal, guiding scientists in the next steps of their investigations. Moreover, simulations of cosmic events can benefit from AI by enabling real-time adjustments to models based on actual observations. This iterative approach allows for rapid hypothesis testing, making it possible to explore a range of scenarios about the universe's creation more efficiently. In addition, AI can assist in recognizing and classifying celestial phenomena, such as supernovae or distant galaxies, adding depth to our understanding of the universe's timeline and structure. The role of AI and machine learning in cosmology is not just about speed, it also opens new horizons for inquiry. As these technologies advance, they may even inspire fresh questions about the origins and mechanics of the universe, pushing us to probe deeper into the fundamental laws of physics. They will serve as powerful allies in our quest to understand the grand story of the cosmos from its very beginning. Education systems can play a crucial role in making complex topics like the universe originating from nothing more accessible. First, teachers can start by linking this advanced concept to familiar ideas. By explaining how something can arise from an absence, educators might ask students to imagine a blank canvas that eventually transforms into a beautiful painting. This analogy can serve as a springboard for discussing more complex ideas. Next, breaking down the history of cosmological thought can help foster understanding. Discussing how ancient civilizations viewed the universe and how this perspective evolved can provide context. It's beneficial to introduce basic astronomy principles first, such as what the universe is, how galaxies form, and the incredible forces at play, like gravity. Using hands-on activities can also enhance learning. For instance, demonstrating how expanding space works with balloons can vividly illustrate how the universe may expand from a singular point. Visual aids, videos or simulations that depict the Big Bang Theory or cosmic inflation can captivate students, helping them visualize concepts that are otherwise abstract. Moreover, encouraging critical thinking and discussions allows students to engage directly with the material. By fostering an environment where questions about existence and the nature of reality can be explored without judgment, educators can encourage a deeper curiosity about the universe. Finally, integrating interdisciplinary approaches, melding physics with philosophy, can motivate students to explore not just the scientific aspects, but also the profound implications of a universe that may have emerged from nothing. This interplay can ignite passions for both science and the exploratory questions that drive human thought. Through these methods, education systems can demystify advanced cosmological concepts and inspire a greater understanding of our universe. Public perceptions of the universe's origins have undergone a significant transformation over the decades, shaped largely by groundbreaking scientific discoveries. In ancient times, many cultures believed in creation myths that explained the universe's beginning in terms of gods or supernatural events. These stories offered simple, relatable explanations for a world that seemed filled with mystery. As time progressed, especially during the Enlightenment, people began to adopt a more scientific viewpoint. Early astronomers like Copernicus and Galileo challenged the notion that Earth was the center of the universe. They demonstrated that the planets revolved around the sun, shifting humanity's perspective from a geocentric view to a heliocentric one. The pivotal moment came in the 20th century with the formulation of the Big Bang theory. This theory suggests that the universe began as an extremely hot and dense point and expanded rapidly. Observations of cosmic background radiation, remnants from that early moment, provided strong evidence for this concept. As people learned about this model, the understanding of the universe's beginnings moved from mythical explanations to a narrative grounded in objective observation and reason. The discovery of galaxies and the observation that they are moving away from one another further cemented the idea of an expanding universe. This concept not only enhanced interest in cosmology, but also sparked questions about what existed before the Big Bang. This shift initiated a quest for deeper knowledge about the universe's birth, nature, and the laws governing it. Recently, advancements in technology and astrophysics have introduced ideas like dark matter and dark energy, which suggest that most of the universe is made up of things we cannot see or fully understand. These theories have complicated the narrative, leading to a more nuanced perception of the origins of our universe. The public is increasingly aware that our understanding is still evolving, recognizing that the universe is both vast and enigmatic. As new discoveries emerge, curiosity only grows. Today, many people not only accept the scientific explanations, but are also fascinated by them, driving interest in science and space exploration. The evolution of ideas around the universe's origins exemplifies humanity's ongoing journey towards understanding our place in the cosmos. Cosmic horizons act as boundaries, preventing us from seeing beyond certain points in the universe. Imagine standing by the edge of a vast ocean where the horizon limits your view of what lies beyond. In the universe, these horizons define the limits of our observable area, meaning that there is a distance beyond which light has not yet reached us, due to the finite speed of light and the expansion of the universe. At the very moment when the universe began, approximately 14 billion years ago, it was hot and dense, filled with energy and matter. As it expanded, the light from that early state traveled through space, but some of it has not had enough time to reach us because of the universe's ongoing expansion. Thus, there are regions so distant that any light emitted from them has not yet had the chance to get to us, creating a sort of cosmic fog. This limitation is significant when we attempt to learn about the universe's beginnings. We can gather some information from ancient light, known as the cosmic microwave background radiation left over from the early universe, but there are countless regions we cannot study. We cannot observe everything that happened, nor can we access first-hand information from the initial events. Consequently, our understanding of the universe's birth is built on inferences and models rather than direct observation. Cosmic horizons limit our knowledge not by what exists, but by the very nature of space and time itself. They restrict our view and strand much of the early universe in a realm of the unknown, reminding us of the vast mysteries still waiting to be unraveled. Beyond the observable universe, where our instruments cannot detect light or other signals, lies a vast realm of speculation and intrigue. One prominent theory is that the universe is infinite, stretching far beyond what we can see. In this view, beyond our observable limits, the cosmos continues endlessly, filled with more galaxies and phenomena we have yet to explore. Another possibility is that the universe is part of a larger multiverse. Imagine each universe as a bubble in a vast sea, where each bubble can differ in properties and laws of physics. In this scenario, our universe is just one of countless others, each possibly hosting its own unique versions of reality. This concept challenges our insights about existence, suggesting there might be universes where the familiar rules of space and time play out differently. These ideas about the universe's unknown regions also touch on the concept of nothing. Traditionally, nothing is considered the absence of anything, no space, no time, and certainly no matter. Yet in quantum physics, nothing can sometimes bubble with activity, leading to fleeting particles springing into existence. This challenges our conventional ideas about voids and the absolute absence of existence. Thus, thinking about what lies beyond the observable universe encourages us to rethink these fundamental concepts. As we delve deeper into the mysteries of the cosmos, we begin to see that what we perceive as nothing might hold more surprises than we initially believe. Understanding this relationship not only expands our view of the universe, but also deepens the enigma of existence itself. Cosmic inflation refers to a rapid expansion of the universe that occurred just after the Big Bang. Imagine the universe right after its creation, extremely small, hot, and dense. Then, in a tiny fraction of a second, it underwent an explosive growth spurt, expanding much faster than the speed of light. This period is thought to have spread the universe from a size smaller than a proton to many times larger than our current observable universe. This concept is crucial because it helps explain several key observations. Without inflation, some features of our universe wouldn't make sense. For instance, the uniformity of the cosmic microwave background radiation, which is the afterglow of the Big Bang, suggests that different regions of the universe share similar temperatures. Inflation provides a mechanism for this uniformity by stretching out spatial areas that were once in contact, smoothing out any irregularities, and allowing for a relatively even distribution of energy. Inflation also addresses the problem of how the universe could appear flat, meaning its shape and structure are balanced in such a way that there is no overall curvature. This perfect flatness could have emerged as a result of the inflationary phase, as regions expanded evenly in all directions. Overall, cosmic inflation is a key piece in understanding how the universe evolved from an extremely hot, dense state to the vast cosmos filled with galaxies, stars, and planets that we observe today. It sets the stage for the later developments in the universe, guiding the structure and distribution of matter we see around us now. Inflation models present fascinating ideas about how the universe might have transitioned from a state often described as nothing into the vibrant cosmos we see today. To understand this, we can start by pondering the concept of nothing. In this context, it doesn't literally mean an empty void. It refers to a state where energy, matter, and space as we know them did not yet exist. One popular model suggests that before the Big Bang, the universe was in a highly energetic state filled with fluctuations. These fluctuations could happen in what is termed quantum fields, which are like invisible fields that permeate all space. In this view, a tiny region of these fields could suddenly gain a vast amount of energy. This event would act like a spark, triggering rapid expansion, commonly known as inflation. The idea is that this sudden burst of energy caused space itself to stretch enormously, effectively transitioning from this pre-Big Bang condition to a universe filled with matter and energy. Another model proposes that the universe could emerge from a false vacuum state. In this case, the vacuum isn't really empty. It contains a lot of energy that doesn't manifest as matter. Imagine a bubbling pot of water. Before it boils, it appears calm, but energy rises within it. If this false vacuum were to become unstable, it could release energy, again leading to inflation and the birth of the universe as we perceive it. Some theories also introduce the notion of multiple universes. In this grander picture, our universe could represent just one bubble in a vast ocean of other universes. The transition from nothing could occur through a mechanism where pockets of energy spontaneously give rise to new universes through inflationary processes. While these models vary, they share a common thread. They all propose that even from a state described as nothing, the universe can arise through complex interactions and fluctuations in energy and fields. Each approach helps scientists unravel the mysteries surrounding the origins of our universe, though conclusive evidence is still a pursuit within the scientific community. Ultimately, these models invite us to think about the universe's beginnings in predominantly new and intriguing ways. Entropy is a key concept that helps us understand how the universe evolved from a state of nothing to its current complexity. In simple terms, entropy refers to the amount of disorder or randomness in a system. When the universe was in its earliest moments, it was extremely hot and dense, a condition often called the Big Bang. In this state, everything was packed tightly together, representing low entropy because the arrangement was highly ordered. As the universe expanded and cooled, this initial order began to break down. Matter and energy spread out, leading to increased entropy. Picture a container filled with gas. When the gas molecules are all clustered in one corner, the system has low entropy. As you let the gas spread out and fill the entire container, the disorder increases, thus raising the entropy. This gradual shift toward greater disorder in the universe allowed for the formation of stars, galaxies, and eventually the diverse structures we see today. Entropy didn't just increase randomly, it also played a crucial role in shaping the pathways of development. As matter condensed under gravity, forming stars and galaxies, energy was released in various forms, such as light and heat. This release of energy is an essential part of how order arises in local systems, even as the overall entropy of the universe rises. In this way, entropy is not just about disorder, it's a fundamental driver of change in the universe. The flow from a highly ordered state to one with more disorder aligns with the second law of thermodynamics, which states that entropy in an isolated system tends to increase over time. Thus, while the universe may begin in a condition close to nothing or a singular state, the ongoing increase in entropy underlies the complexity and vastness we experience today, allowing for the creation of everything from stars to planets and eventually life. Entropy is a fundamental concept in understanding how the universe evolves and grows more complex. At its core, entropy measures the level of disorder or randomness within a system. In the beginning, the universe was incredibly hot and dense, a state of very low entropy. As it expanded, this initial uniformity gave way to complexity, the formation of galaxies, stars, and eventually planets. As matter began to clump together due to gravitational forces, localized areas of low entropy emerged. Think of this process like a chaotic crowd gradually forming into distinct groups. While the overall disorder might increase, pockets of order develop simultaneously. These clumps create stars, which ignite with nuclear fusion, generating elements and energy that feed into larger structures. As the universe continues to evolve, entropy tends to rise overall. For example, when stars die, they often explode in supernovae, scattering elements throughout space, creating new clouds of gas and dust. This contributes to the overall disorder as matter spreads out, yet simultaneously leads to new cycles of star formation, causing even more complexity over time. However, it's essential to realize that while the universe as a whole becomes more disordered, the local regions, like the formation of living systems on Earth or the birth of new stars, showcase how complexity can emerge from simple initial conditions. In the grand scheme, entropy reflects the balance between the chaotic spreading of energy and the beautiful structures that arise from it. The universe grows not just in size, but in intricate potential, laying the groundwork for the diversity of phenomena we observe today. Scientists utilize computer simulations as powerful tools to explore and test their hypotheses about the universe's origins. At the heart of this method is the understanding that the universe is governed by various physical laws, including gravity and thermodynamics. By translating these complexities into a set of algorithms, researchers can create models that simulate cosmic events from the very beginning. Imagine the early universe as a vast, chaotic space filled with energy and particles, all interacting in ways that led to the formation of galaxies, stars, and planets. Scientists build simulations that mimic these conditions, allowing them to observe how matter evolves over time. By adjusting variables within the simulation, such as the density of matter or the strength of gravitational forces, researchers can see how these changes influence the development of cosmic structures. Moreover, simulations can serve to recreate different scenarios, such as the Big Bang, the explosive event that marked the universe's beginning. Through these recreations, scientists can analyze patterns and behaviors that align with what we observe today, such as the distribution of galaxies or cosmic microwave background radiation. The results can either support existing theories or challenge them, sparking further investigation and refinement. Scientists also compare the outcomes of their simulations with actual astronomical data gathered from telescopes and satellites. If a simulation produces results that closely match observations, it adds weight to the hypothesis being tested. Through iterative processes, where simulations are constantly refined and compared against new data, scientists gradually enhance their understanding of cosmic origins. Ultimately, these computer-based explorations provide insights that are both imaginative and grounded in scientific rigor, allowing us to probe the mysteries of the universe's beginnings in ways that would be impossible to achieve through observation alone. The moments right after the universe came into existence are among the most fascinating and complex times in cosmic history. Breakthroughs in understanding this period have come from various fields of science, particularly astrophysics and particle physics. Researchers believe that the universe began with an event known as the Big Bang. During this initial explosion, the universe expanded rapidly from a state of extremely high density and temperature. One important advancement is the development of computer simulations that mimic these early moments. Scientists use these simulations to recreate conditions of the early universe, including the formation of basic particles such as protons and neutrons. These particles then began to combine into simple atoms, primarily hydrogen and helium. Observations of the cosmic microwave background radiation, which is faint light left over from that hot early state, provide crucial clues about what happened shortly after the Big Bang. Another significant breakthrough is the use of particle accelerators, where scientists can recreate the very high energy conditions that existed at the beginning of the universe. These experiments help to validate theories about fundamental forces and particles, giving insights into how matter and energy interacted during those first moments. The discovery of the Higgs boson, for instance, has enhanced our understanding of how particles acquire mass, which is critical to understanding the fabric of the early universe. Moreover, advancements in observational astronomy, such as studying the distribution of galaxies and cosmic structures, have improved our understanding of how the universe evolved from a hot, dense state to the vast cosmos we see today. These observations provide evidence that supports various models of cosmic inflation, which theorizes how and why the universe underwent rapid expansion shortly after the Big Bang. Together, these breakthroughs form a comprehensive understanding of the universe's birth and the intricate dance of particles and forces that shaped its early moments, providing a clearer picture of our cosmic origins. Artists often take the complex scientific theories about the universe emerging from nothing and express them in a way that sparks imagination and emotion. These theories suggest that the universe may have begun from a state of absolute emptiness, where, through processes unknown, energy and matter began to exist. In various artworks, you may find representations of vast, dark spaces filled with shimmering stars, symbolizing the transition from nothingness to a vibrant universe. These pieces can evoke feelings of wonder, mystery, and even the fragility of existence. Some artists may choose to visualize the Big Bang, the moment when the universe expanded from this seemingly empty state, through dynamic patterns and explosive colors, capturing the intensity and drama of creation. Others might focus on the idea of a void, creating stark contrasts between dark and light to emphasize the surreal shift from nothing to something. As artists delve into these themes, they often weave in philosophical questions. What does it mean for something to come from nothing? How does this challenge our perceptions of reality and existence? These inquiries inspire their work, inviting viewers to reflect on their own understanding of life and the cosmos. Through their interpretations, artists bring to life the awe-inspiring and often unfathomable concepts of scientific theories, making them accessible and relatable to a wider audience, while also provoking deeper thought about our place in the universe. Storytelling techniques can significantly enhance the presentation of intricate cosmological ideas by making them more relatable and engaging. At its core, effective storytelling takes complex concepts, which might otherwise feel abstract or intimidating, and weaves them into narratives that evoke curiosity and understanding. By framing cosmology within a story, audiences can connect emotionally and intellectually with the material. One powerful technique is the use of characters. For example, presenting a scientist or explorer as the protagonist can humanize the journey of discovery in the universe. This character can face challenges, make breakthroughs, and evoke wonder about the cosmos, allowing viewers to see scientific progress as a dynamic and thrilling adventure instead of dry facts and figures. Another important aspect is the use of analogies and metaphors. By comparing complex cosmic phenomena to everyday experiences, audiences can grasp difficult ideas more easily. For instance, describing the expansion of the universe as blowing up a balloon helps illustrate how galaxies move apart as space itself stretches, creating a clearer picture in the mind. Additionally, a narrative structure can provide context that aids understanding. By building a story with a clear beginning, middle, and end, such as starting with early human observations of the stars and culminating in modern astrophysics, viewers can appreciate how our understanding of the universe has evolved over time. This sequential unfolding mirrors scientific discovery, making the material both educational and captivating. Visual storytelling is also key. Cosmic events such as supernovae or the formation of black holes can be illustrated with stunning graphics. Visuals not only enhance comprehension but stir awe, allowing audiences to experience the beauty of the universe firsthand. Ultimately, when complex cosmological ideas are presented as part of a captivating narrative, they become accessible and inspiring. Storytelling invites viewers on a journey of exploration, fostering a deeper appreciation for the vastness and mysteries of the universe while simplifying the scientific concepts that underpin our understanding of reality. Evolutionary cosmology presents a fascinating perspective on the universe and its origins, emphasizing a dynamic and ever-changing cosmos rather than a static one. Traditional views often center around a singular moment of creation, such as the Big Bang, which marks a specific beginning of time and space. In contrast, evolutionary cosmology approaches the universe as a process that unfolds over vast timescales, much like biological evolution. At the core of this idea is the belief that just as life evolves through natural selection and adaptation, so too does the universe itself undergo transformations. This perspective suggests that the cosmos is not merely a backdrop for events, but an active participant in its own evolution. It sees the formation of galaxies, stars, and planets as part of a continual development, shaped by the laws of physics and cosmic interactions. One significant difference from traditional cosmology lies in the implications for existence itself. While classical views often imply a defined starting point and sometimes suggest a predetermined fate, evolutionary cosmology posits that the universe could evolve in various ways influenced by countless factors. This means that galaxies can form and evolve, die out, and even lead to the creation of new structures, a reflective process of renewal over extensive epochs. Moreover, evolutionary cosmology can accommodate the idea that the universe may not be a solitary entity, but part of a larger multiverse, where different regions might experience their own unique evolutionary pathways. This perspective encourages curiosity about the future, prompting questions about how the cosmos will continue to change and develop long after our current moment. Evolutionary cosmology pushes us to see the universe as a living entity, characterized by ongoing change, adaptation, and complexity, contrasting with the more fixed historical narrative often associated with traditional cosmological models. Evolutionary cosmology is a fascinating way of understanding both the universe and its origins by examining how everything has emerged and developed over time. When we talk about nothing in this context, we don't mean the absence of everything. Instead, we refer to a state before the universe began, a kind of cosmic emptiness where conventional matter, energy, time, and space did not exist yet. Imagine the universe as a grand story unfolding over billions of years. Before this story began, there was a state of potential, sometimes described as a vacuum. This vacuum can be thought of as a fertile ground where the seeds of reality might emerge. It's not a void in the traditional sense. Rather, it's filled with possibilities and quantum fluctuations. These fluctuations are tiny changes that can occur even in this seemingly empty space, which might eventually spark the processes that lead to the universe as we know it. In evolutionary cosmology, this initial nothing could lead to a state ripe for evolution, where particles began to form, merge, and evolve into atoms, stars, galaxies, and eventually planets. Over billions of years, these structures change, grow, and develop complexity, much like biological evolution on Earth. Throughout this process, the universe is continually influenced by the laws of physics, which dictate how everything interacts. Thus, when we incorporate the concept of nothing into evolutionary cosmology, we see it not as a finality, but as a crucial starting point, the stage where potential transitions into creation. This makes the universe a dynamic tapestry that evolves from a state of nothing to a rich and structured cosmos, constantly changing and expanding. Understanding this journey helps us appreciate our place in the universe and how everything, including ourselves, is a part of this ongoing cosmic evolution. In the quest to understand the universe, scientists have long grappled with various theories that describe its fundamental forces and particles. One of the most ambitious goals in modern physics is to create a framework that unifies these disparate theories into a cohesive understanding. Among the leading contenders is string theory, which posits that the smallest components of the universe are not point-like particles, but tiny vibrating strings. These strings can create all the different particles we observe in nature based on their vibrational modes. This theory seeks to merge quantum mechanics and general relativity, suggesting that at the tiniest scales, the laws of physics might behave differently. Another framework is loop quantum gravity, which offers an alternative approach. Rather than relying on strings, this theory attempts to quantize space itself, suggesting that space is made up of tiny loops. These loops create a network that is woven into the fabric of the universe. By quantizing gravity directly, loop quantum gravity aims to solve differences between the theories of gravity and the quantum world, striving for a unified description of the cosmos. Then there is the concept of the multiverse, which emerges from various theories, including cosmic inflation. This idea proposes that our universe is just one of many, each with its own laws of physics. The multiverse perspective changes how we think about the cosmos, suggesting that what we perceive as our singular reality is just a slice of a much larger and more complex existence. Finally, researchers are also exploring the idea of emergent gravity. This concept proposes that gravitational effects are not fundamental, but arise from more basic microscopic interactions. This perspective is revolutionary, as it suggests that space, time, and gravity may emerge from an underlying framework of quantum physics and information theory. As scientists continue to investigate these frameworks and their implications, they strive for a more complete understanding of the universe, one that may one day unify the diverse theories into a single narrative of existence. The journey is complex, filled with challenges, yet it drives forward the boundaries of human knowledge and our understanding of everything that surrounds us. The idea of a universe emerging from nothing is a profound topic in modern cosmology. To understand this concept, we first need to define what we mean by nothing. Philosophically, nothing implies the absence of anything, including matter, energy, space, and time. In the realm of science, however, nothing can be more complex. Some frameworks in cosmology suggest that our universe began as a quantum state, a kind of emptiness that is not truly vacant but rather teeming with potential. In this perspective, the emptiness of a vacuum is not devoid of activity. Instead, it's filled with fluctuating energy and virtual particles that pop in and out of existence, facilitated by the rules of quantum mechanics. This leads to the intriguing possibility that the universe could have spontaneously arisen from such a vacuum fluctuation. It's like stirring a pot of ingredients that seem to just sit still, but when you add the right amount of heat, they mix and transform into something new. Similarly, certain theories propose that a shift or event in this quantum state could have sparked the Big Bang, leading to the expansion of space and the creation of matter we observe today. Another perspective is related to the concept of inflation. This theory posits that in the very early moments of the universe, an exponential expansion occurred. This rapid growth could have resulted from fluctuations in energy, effectively creating space and all its contents from what might have seemed like nothing. However, these ideas still leave many questions unanswered. For instance, what caused the initial fluctuation? What exists beyond our universe? While these frameworks offer insights into how a universe can arise from nothing, they remind us that many mysteries remain about the very origins of existence. Each theory opens new avenues of thought, inviting further exploration into the nature of our universe and the strange rules that govern its birth and evolution. The quest to understand the universe's beginnings is driven by a deep curiosity about our own existence and the nature of everything around us. For scientists, this inquiry often stems from the desire to piece together the physical laws and forces that have shaped the cosmos. They are captivated by the idea of uncovering the fundamental principles that govern the universe, including how everything emerged from what is often described as a singular event known as the Big Bang. Philosophers contribute to this exploration by pondering the implications of such beginnings. They ask profound questions about purpose, existence, and reality itself. What does it mean for humanity to be here at all? Are we simply a product of chance, or is there a larger narrative at play in the universe's fabric? This intersection of scientific inquiry and philosophical reflection enriches the dialogue, feeding the quest for knowledge. As researchers delve into the cosmic microwave background radiation, which is like the afterglow of the early universe, they are piecing together a puzzle that has captivated minds for centuries. Each discovery leads to new questions, invoking a sense of wonder and fostering a desire to understand not just the mechanics of how stars and galaxies formed, but also the significance of our tiny place in a vast and ancient cosmos. This intertwining of scientific discovery and philosophical exploration reflects a fundamental human drive: to seek understanding, to embrace the unknown, and ultimately, to make sense of our extraordinary universe. Our understanding of the universe's origin is often colored by personal beliefs, which can shape how someone perceives scientific evidence or philosophical ideas. For many individuals, cultural backgrounds, spiritual teachings, and life experiences play a significant role in forming their views. For instance, someone raised in a religious context may embrace creation stories that describe how a higher power brought the universe into existence. These narratives often provide meaning and purpose, leading some to interpret scientific discoveries through a lens that aligns with those beliefs. On the other hand, people who prioritize scientific inquiry might focus on theories such as the Big Bang. This concept explains that the universe started from a hot, dense state and has been expanding ever since. However, even among those who lean towards scientific explanations, belief systems can still influence interpretations. For example, some may view the intricacies of the universe as evidence of a design, while others might see it purely as a series of random events. Furthermore, emotions and psychological factors can also come into play. Individuals may feel a sense of awe or fear when considering the vastness of the universe, leading them to seek answers that resonate with their feelings. This personal connection to the cosmos can affect how they process information and make sense of the unknown. Personal beliefs act as a lens through which many people view the origins of the universe. Whether through spiritual, scientific, or philosophical frameworks, these beliefs not only shape interpretations, but also give people a way to connect with and find meaning in the grand story of existence. Throughout history, many brilliant minds have contributed to our understanding of the universe's origins. One of the foremost figures is Albert Einstein, whose theory of relativity revolutionized our view of time, space, and gravity. His work laid the groundwork for modern cosmology and led to questions about how the universe began. Building on Einstein's ideas, Georges Lemaitre proposed what is now known as the Big Bang theory in the early 20th century. He described the universe as expanding from a primordial state, suggesting that it began from a hot, dense point, an idea that fundamentally changed our understanding of cosmic origins. Another key contributor is Edwin Hubble, who provided observational evidence for Lemaitre's theory. By discovering that galaxies are moving away from us, he demonstrated that the universe is expanding, supporting the concept that it had a beginning. In more recent times, Stephen Hawking made significant contributions by exploring the nature of black holes and singularities. His research provided insights into the conditions that may have existed at the moment the universe began and suggested that time itself might have originated with the Big Bang. Furthermore, physicist Alan Guth introduced the concept of cosmic inflation, proposing that a rapid expansion occurred just after the Big Bang, which explains many uniformities observed in the universe today. His work has become a crucial part of the modern understanding of the universe's beginning. These thinkers, among others, have shaped the discourse on how the universe came to be, each adding their unique perspective and findings. Their ideas have inspired generations to explore the cosmos and the very fabric of reality. The contributions of early astronomers and physicists have laid the essential groundwork for our current understanding of the universe. Think of these pioneers as explorers who ventured into the unknown, laying out maps that guide today's scientists. For instance, the work of figures like Galileo, who used his telescope to study celestial bodies, fundamentally changed our perspective of the cosmos. He revealed that the Earth is not the center of the universe, which shifted the paradigm of how we view our place among the stars. Later, the development of the theory of relativity by Albert Einstein revolutionized the way time and space were understood. It introduced concepts that showed how mass and energy influence the fabric of the universe, leading to new insights about cosmic phenomena such as black holes and the expansion of space. This theory has not only transformed theoretical physics, but has also become a crucial framework for modern cosmology. Moreover, Edwin Hubble's observations provided strong evidence for the expanding universe. He discovered that galaxies are moving away from us, and the farther away a galaxy is, the faster it seems to be receding. This observation supports the notion that the universe began from a hot, dense state and has been expanding ever since, commonly referred to as the Big Bang theory. Hubble's findings ushered in a new era of cosmological research, prompting astronomers to investigate the origins and fate of the universe. Today, these foundational ideas inform ongoing research. Scientists are delving into the nature of dark matter and dark energy, which compose the majority of the universe, yet remain elusive. Future research directions are aiming to unravel these mysteries, extending the legacy of earlier contributions. Projects like advanced telescopes and satellites are set to enhance our observations, allowing us to probe deeper into the cosmos than ever before. The contributions of these early figures not only shaped our current understanding, but also inspire a quest for knowledge that drives astronomical research today. Their legacies continue to guide us as we strive to answer some of the most profound questions about the universe and our existence within it. Advancements in technology play a crucial role in uniting scientific understanding and spiritual perspectives about the universe's origin. One of the most significant contributions is in the field of astronomy. With powerful telescopes, both on the ground and in space, we can observe galaxies billions of light-years away. This capability allows us to witness the cosmic events that led to the formation of stars and planets, providing a clearer picture of how the universe began, which can influence spiritual beliefs about creation. Furthermore, technology enables us to gather and analyze vast amounts of data about the universe. Instruments such as high-energy particle colliders explore the fundamental particles that make up matter, shedding light on the conditions that existed during the very first moments of the universe. This scientific inquiry into the building blocks of existence can resonate with spiritual questions about the nature of reality and what it means to be part of something larger. Moreover, advancements in communication technology allow scientists and spiritual thinkers to share their ideas more easily than ever. Online platforms and social media have created spaces for dialogue where different perspectives can be exchanged. This exchange encourages a richer understanding of both scientific discoveries and spiritual insights. In addition, technologies like virtual reality can simulate cosmic events, letting people experience the wonders of the universe in immersive ways. Such experiences can evoke feelings of connection and awe, bridging what can sometimes feel like a divide between science and spirituality. When individuals are presented with stunning visualizations of cosmic phenomena, they may find their own spiritual or philosophical beliefs evolving alongside scientific discoveries. Ultimately, technology not only advances our knowledge of the universe, but also serves as a bridge, fostering conversations between science and spirituality. As we continue to explore the origin of our universe, the synergy between these perspectives can lead to profound insights about our place in the cosmos. The question of how the universe could emerge from nothing has sparked significant debate at the crossroads of science and faith. This discussion often revolves around two main ideas: the scientific understandings of the universe's origins and the philosophical or spiritual interpretations of creation. On the scientific side, researchers propose that our universe began with an event known as the Big Bang. This theory asserts that space, time, and all matter started from an incredibly dense point. From this moment, the universe expanded and evolved into what we observe today. However, what exists before this event remains a mystery. Scientists explore concepts such as quantum fluctuations, where tiny bursts of energy in a vacuum could potentially give rise to particles, and ultimately, the universe itself. This idea poses challenging questions. What does nothing truly mean, and can something emerge from a complete void? In contrast, many religious perspectives offer an interpretation of creation that is rooted in belief rather than empirical evidence. These views often describe an intentional act of a divine being bringing the universe into existence. For believers, the idea of creation ex nihilo, or creation from nothing, is a foundational concept conveying the power and purpose behind existence. This perspective emphasizes faith, suggesting that human understanding may not encompass the full nature of divine action. The dialogue between these two realms raises essential questions about the limits of human knowledge. As science continues to uncover the mechanisms behind cosmic origins, some suggest that these discoveries can coexist with faith. Others argue that science and faith serve different purposes and that conflating them can lead to misunderstandings. Moreover, discussions about ethics and the implications of discovering how the universe began also emerge. Science might explain the how, but faith often seeks to address the why. These ongoing debates not only challenge our understanding of the universe, but also encourage a shared exploration of existence, reality, and the nature of belief itself. By examining and respecting these differing perspectives, we move closer to understanding the profound and complex questions that have resonated throughout human history. Understanding the universe's beginnings offers profound insights that can enrich our daily lives in several meaningful ways. At its core, this exploration connects us to a larger story, reminding us that we are part of something much bigger than our individual experiences. When we learn about how the universe formed from a single, incredibly dense point and evolved over billions of years, it fosters a sense of curiosity. This curiosity can inspire us to seek knowledge in our own lives, encouraging lifelong learning and a deeper appreciation for the world around us. Moreover, understanding the origins of the universe can spark discussions about science, philosophy, and our place in existence. These conversations can lead to new perspectives and help build community bonds as people come together to explore big questions about life and existence. On a practical level, the scientific methods developed to study the cosmos, like observation, experimentation, and critical thinking, can be applied to everyday problem solving. Embracing these methods can empower individuals to approach challenges with a more analytical mindset. This skill is useful not just in scientific endeavors, but also in personal and professional contexts. Lastly, recognizing that we share a common origin with all of humanity can promote compassion and empathy. Understanding that the elements of our bodies were formed in stars and that we are part of an intricate web of existence can remind us to appreciate our interconnectedness. This perspective can encourage us to act thoughtfully and responsibly in our communities and towards the environment, fostering a sense of stewardship for our planet and future generations. Exploring the beginnings of the universe can transform how we see ourselves and our responsibilities in the world. It ignites curiosity, enhances critical thinking, and promotes a sense of connection that enriches our daily lives. Exploring the universe's emergence from what we call nothing raises profound questions that resonate deeply within our cultures and societies. This concept challenges humanity's understanding of existence itself, prompting discussions that extend far beyond science. When we talk about nothing, we're referring to a state devoid of matter, energy, or even the fabric of space-time as we know it. This idea can spark not only scientific inquiry, but also philosophical and theological exploration. As we delve into these mysteries, cultures may start to re-evaluate their beliefs about the origins of the universe. Many religions have creation stories explaining how everything came into being. New scientific insights could lead to dialogues about reconciling these ancient narratives with contemporary understandings of cosmology. Such conversations can foster a greater sense of unity among different belief systems, as many may seek common ground in our shared curiosity about existence. The societal impact is also significant. When people learn about the universe's beginnings, it can ignite a sense of wonder and curiosity, inspiring young minds to pursue careers in science and technology. This inspiration helps cultivate a society that values exploration and knowledge. Furthermore, as we grapple with complex ideas about existence, we also confront ethical questions about our role in the universe. Are we merely observers, or do we have a purpose in this vast cosmic tapestry? These reflections can influence how we view ourselves and our responsibilities towards each other and the planet. Moreover, engaging with the concept of nothingness can push societies to confront existential anxieties and questions of meaning. What does it mean to exist in a universe that has evolved from a void? This contemplation could lead to a more philosophical discourse in public spheres, perhaps encouraging a search for deeper understanding and connection in our lives. This quest for knowledge and meaning could reinforce community bonds, as sharing these discussions fosters a collective journey of discovery. The exploration of the universe's origins from nothing reaches far beyond the scientific realm. It intertwines with cultural narratives and societal values, encouraging dialogue, inspiring future generations, and prompting us to consider our place in the cosmos. Through this journey, we not only seek answers about our universe, but also engage in a profound examination of ourselves and our interconnectedness. Historically, poetry has been a powerful medium for exploring profound questions about existence and the concept of nothing in relation to the universe. Poets often delve into the feelings and ideas surrounding our place in the cosmos, pondering what it means to exist amidst the vastness of space. Many early poets used nature as a backdrop to reflect on these existential themes. They observed celestial bodies like stars and moons and asked questions about their own lives in relation to the infinite universe. This connection to the natural world enabled them to express feelings of awe, insignificance, and wonder, creating a sense of unity between the personal and the cosmic. As time went on, poets grew increasingly interested in the philosophical implications of nothing. Some saw nothingness as a source of fear, grappling with the idea of a void that exists beyond our understanding. Others viewed it as a blank canvas, a space where creation could flourish, emphasizing the idea that from nothing, everything can emerge. This duality reflects the struggle between despair and hope, a push-pull dynamic that resonates throughout literary history. In more modern poetry, existential themes became intertwined with scientific discoveries about the universe. Poets began to use concepts from physics and cosmology, referencing ideas like the Big Bang or black holes, to explore the limitations of human understanding. These modern verses often reflect on how tiny and fleeting human existence is compared to the grand scale of the universe, yet capture a sense of craving for meaning in that brief flicker of life. Through various forms and styles, poetry has served as a vessel for humanity's search for meaning. It has captured the uncertainty of existence, the confrontation with the void, and the inevitable curiosity that drives us to explore the unknown. In all these explorations, poets harness emotions and ideas to help articulate the complexities of existence and the relationship we share with the universe, offering glimpses into what it feels like to be both utterly small and remarkably significant in an ever-expanding cosmos. Poetic interpretations can enrich scientific discussions about the universe's origin by adding layers of meaning and emotional depth. While science focuses on measurable facts and logical explanations, poetry captures the wonder and mystery surrounding the cosmos. A poem might express the awe of gazing at the stars or the profound feeling of connection to the vast universe, evoking emotions that statistics and theories alone may not convey. Moreover, poetry often uses metaphor and imagery to communicate complex concepts in relatable terms. For example, instead of just describing the Big Bang with equations or technical jargon, a poem might evoke the image of a seed bursting forth into life, illustrating the idea of one moment giving birth to everything we know. This kind of language invites a broader audience to engage with scientific ideas, making them more accessible and memorable. Additionally, the interplay between science and poetry can spark curiosity and inspire new questions. Poetic interpretations can serve as a starting point for scientific inquiry, leading individuals to explore the universe's mysteries through a different lens. This combined approach can create a richer understanding and appreciation of not just how the universe came to be, but also why it captivates us so deeply. By embracing both perspectives, we celebrate the quest for knowledge while honoring the profound emotions tied to our existence within the cosmos. The foundations of modern cosmological theories were built on the insights and discoveries of several key historical figures. One of the earliest was the Greek philosopher Aristotle, who proposed a geocentric model, placing Earth at the center of the universe. His ideas, while incorrect, dominated thinking for many centuries. Fast forward to the 16th century, and we encounter Nicholas Copernicus. He revolutionized the field by suggesting a heliocentric model, which positioned the Sun at the center of the solar system, changing the course of astronomy. This shift not only challenged existing beliefs, but also sparked further inquiry. Building on Copernicus's work, Johannes Kepler later introduced his laws of planetary motion. These laws described how planets move in elliptical orbits, providing a more accurate framework for understanding celestial mechanics. Kepler's work laid important groundwork for Isaac Newton, who in the 17th century formulated the law of universal gravitation. Newton demonstrated how the same gravitational force that causes objects to fall on Earth also governs the motion of celestial bodies. In the early 20th century, Albert Einstein brought a transformative perspective with his theory of general relativity. This theory explained gravity not just as a force, but as the curvature of space-time caused by mass. Einstein's ideas redefined how we understand the universe, leading to predictions about the behavior of objects in extreme conditions, such as black holes and the expansion of the universe. Expanding upon these theories, Edwin Hubble provided observational evidence that the universe is indeed expanding. His findings revealed that distant galaxies are moving away from us, which suggested that the universe was once much smaller and led to the formulation of the Big Bang theory. These figures, Aristotle, Copernicus, Kepler, Newton, Einstein, and Hubble, each contributed crucial pieces to the puzzle, collectively shaping our understanding of the cosmos as a dynamic and ever-evolving expanse. Their legacies continue to inspire scientific exploration and deepen our grasp of the universe today. The idea that our universe might emerge from nothing is a profound concept that has evolved from the work of many brilliant minds throughout history. Initially, philosophers and early scientists pondered the nature of existence and cosmology without the support of modern tools or advanced knowledge. They questioned what existed before everything we see today. In the early 20th century, a pivotal moment occurred with the discovery of the expanding universe. Edwin Hubble observed that galaxies are moving away from us, providing evidence that the universe had a beginning, which stirred questions about its origin. In this context, a model emerged suggesting that perhaps the universe started from an extremely hot and dense state, sometimes referred to as the Big Bang. This event marked the beginning of space and time as we understand them. As physicists explored further, they began to consider the concept of nothing. In a scientific context, nothing isn't a simple void. Rather, it refers to a state devoid of conventional matter and energy, but possibly filled with fluctuating fields and virtual particles. Quantum physics introduces intriguing notions where particles can spontaneously arise out of this vacuum due to energetic fluctuations. Building on these foundations, researchers like Stephen Hawking proposed that even time itself may have a limit, suggesting that concepts of before the Big Bang might not even apply. In this framework, the universe's existence could seem to stem from a kind of quantum state that defies our everyday understanding. These ideas intertwine, suggesting that the universe didn't necessarily require a traditional beginning or cause, leading to a revolutionary perspective. Reality, as we perceive it, could emerge from a complex interplay of quantum forces, existing in a state of potentiality rather than a void. Thus, our current understanding is shaped by centuries of inquiry and the fusion of ideas from physics, philosophy, and cosmology, culminating in the fascinating notion that all we know could arise from nothing if we redefine what nothing means in the context of modern science. Understanding the origin of the universe is a journey filled with profound questions and ingenious methods of exploration. Researchers are organizing their next steps around a few key ideas that build upon previous discoveries. One major focus is the study of cosmic background radiation. This faint glow left over from the Big Bang serves as a snapshot of the early universe. Scientists plan to enhance their instruments to analyze this radiation with even greater detail. By examining tiny variations in temperature and intensity, they hope to gain insights into the formation of the first stars and galaxies. Another promising area is the investigation of dark matter and dark energy. These mysterious components make up most of the universe but remain poorly understood. Upcoming experiments aim to gather more data about how they interact with regular matter. By determining their properties, researchers can piece together their roles in shaping the universe's expansion and structure. Additionally, scientists are turning to powerful telescopes and satellites. These advanced technologies will allow for deeper observations of distant galaxies and cosmic events. For example, observing the light from distant stars and galaxies can reveal information about how they have evolved and contributed to the universe's history. Collaborative efforts between global research communities are also predicted to intensify. By sharing data and resources, new theories can arise, supported by a broader range of observations and experiments. This teamwork can accelerate the quest for understanding the universe's origins. Lastly, theoretical physicists are working on new models that bridge quantum mechanics and general relativity. These efforts might lead to fresh insights on what happened during the earliest moments of the universe, where both quantum effects and gravitational forces were at play. Through these diverse approaches, the next steps in researching the universe's origin promise to unveil exciting discoveries and deepen our understanding of how everything began. Emerging technology in space exploration has the potential to fundamentally change how we understand the origins of the universe. With advanced telescopes and spacecraft equipped with cutting-edge instruments, we can probe deeper into space than ever before. These technologies allow us to observe ancient light that has traveled for billions of years, giving us glimpses into the early moments after the Big Bang, when the universe was still forming. New methods of detecting gravitational waves are also opening a new window of exploration. Gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, can tell us about collisions between black holes and neutron stars, hinting at processes that occurred in the universe's infancy. Observing these phenomena helps us piece together a clearer timeline of cosmic events. Furthermore, advancements in artificial intelligence enhance our ability to analyze vast amounts of astronomical data. With these algorithms, we can identify patterns and anomalies in cosmic data that may have been previously missed, allowing scientists to develop new theories about the universe's formation and evolution. As we deploy missions to moons and planets in our solar system like Europa and Mars, we gain additional insights into how life might have originated and evolved, not just on Earth, but potentially elsewhere in the universe. Discovering organic substances or the conditions for life in these places can reshape our understanding of life's probabilities in a cosmic context. With each leap in technology, we are not merely gathering information, but also rewriting our narrative about the universe's beginnings. Each discovery builds on the last, transforming our view from a static picture into a dynamic, evolving understanding of how everything came to be. The more we learn, the clearer the story of the universe's birth and growth becomes, unlocking mysteries that have puzzled humanity for generations. The universe's origin from what we call nothing is one of the most profound mysteries of science. In simple terms, instead of coming from a void filled with nothingness, the universe started from a state where all the potential for everything existed. This idea is much like a seed that contains everything needed to grow into a great tree. It holds incredible potential inside, despite seeming small and insignificant at first. When we connect this to theories of consciousness, a fascinating parallel emerges. Some thinkers propose that just as the universe began with infinite possibilities from a seemingly empty state, human consciousness might operate in a similar fashion. It could be understood as emerging from a kind of fundamental essence or awareness that is present in all of us, waiting to express itself. The notion here is that both the universe and consciousness share a common source of potentiality. Moreover, as the universe expanded and evolved, it became more complex, forming galaxies, stars, and eventually life. In the same way, our minds grow and evolve through experiences and knowledge, intricately weaving thoughts and emotions into the tapestry of our conscious experience. Some theories posit that consciousness could even be a fundamental aspect of the universe, sort of like a universal thread connecting all living things. While these connections remain largely speculative, they invite us to think about the nature of reality itself. Understanding the universe's inception from nothing, alongside exploring consciousness, encourages deep questions about existence, awareness, and the very fabric of our being, a journey that continues to captivate both scientists and philosophers alike. The birth of the universe and the emergence of human consciousness share intriguing parallels that highlight the evolution of complexity from simple beginnings. Both processes begin with a state of singularity, one being the moment of the Big Bang, when all matter and energy were concentrated in an incredibly hot and dense point, and the other representing the initial stages of human development, where basic neural processes lay the groundwork for more advanced thought. As the universe expanded, it evolved from dim cloud-like formations of gas to intricate structures, stars, galaxies, and planets. Similarly, human consciousness began with primitive instincts and reactions, gradually developing into a rich network of thoughts, emotions, and self-awareness. Just as cosmic evolution led to diverse forms of life across different environments, the development of consciousness opened pathways to culture, creativity, and complex social systems. Another parallel can be seen in the concept of interconnectedness. In the universe, galaxies are woven into a vast web of gravitational forces, with each element influencing another. In a similar way, the mind forms connections between neurons, with each experience and thought shaping one's consciousness and understanding of the world. Both phenomena also reflect the idea of reaching a state of balance over time. The universe has found equilibrium through processes like the formation of stars and the cooling of space. Meanwhile, as individuals grow and mature, they strive for a balance between emotions, experiences, and rational thought, seeking harmony within themselves and their surroundings. Lastly, both the universe's birth and the journey of human consciousness are driven by curiosity and a desire to explore. The universe expands and evolves, while human consciousness seeks knowledge, understanding, and meaning. This inherent drive to discover fuels both cosmic evolution and personal growth, proving that the origins of existence and awareness are deeply interconnected threads in the fabric of reality. Exploring the universe's beginnings brings forth a rich tapestry of ethical questions. One major concern is the potential impact of our discoveries on humanity's worldview. As scientists unveil insights about how the universe began, these revelations can challenge deeply held beliefs about existence, creation, and life's purpose. This can lead to a clash between scientific understanding and religious or cultural perspectives, sparking debates about respect and sensitivity towards various beliefs. Another ethical consideration involves the use of technology and its implications. For instance, advanced instruments used to study cosmic phenomena often rely on significant resources and energy. Questions arise regarding the environmental footprint of these technologies and whether the pursuit of knowledge justifies potential harm to our planet. The pursuit of knowledge itself raises dilemmas about access and equity. Scientific research is often expensive, which may limit participation to well-funded institutions and wealthy nations. This raises concerns about whose knowledge is valued and whether insights into the universe will be shared widely or only benefit a privileged few. Moreover, ethical dilemmas extend to the hypothetical consequences of human actions in space. As we search for answers about the universe's dawn, we might encounter opportunities for exploration or colonization of other celestial bodies. This prompts questions about our responsibilities toward those environments and any potential life forms that may exist, emphasizing the need for stewardship rather than exploitation. Finally, the implications of our findings could lead to existential anxieties. If scientists continue to unveil truths about the universe that suggest fragility or insignificance of humanity, it raises ethical considerations on mental and emotional impacts on society. Balancing the pursuit of knowledge with the broader implications of that knowledge requires careful thought and consideration as we delve deeper into understanding our cosmic origins. As scientists delve into the origins of existence, they encounter profound ethical questions that guide their exploration. The journey often begins with the desire to understand how everything came to be, from the smallest particles to vast galaxies. However, this quest raises significant concerns about the implications of such knowledge. Firstly, the act of exploring existence prompts philosophical discussions about the nature of life itself. Researchers must consider what it means to exist and the responsibilities that come with such knowledge. If scientists uncover truths about the beginnings of the universe or life, how might this influence our understanding of humanity's place within it? The methods used in this exploration, particularly in areas like cosmology and biology, demand ethical scrutiny as well. Techniques such as particle collisions in massive accelerators or probes sent to distant planets pose safety and ecological questions. Scientists need to balance the pursuit of knowledge with the potential risks to both our planet and beyond. Will our actions in these explorations impact other environments, possibly harming ecosystems or extraterrestrial forms of life, should they exist? Moreover, societal implications are crucial. Discoveries about the origins of existence could challenge or confirm long-held beliefs in various cultures and religions. Scientists must navigate conversations that respect diverse viewpoints while sharing their findings. Open communication with the public becomes essential to foster understanding and mitigate fear or misinformation. In addition, funding plays a significant role in these explorations. Ethical considerations arise regarding where financial support comes from and how it shapes the research agenda. Scientists are often tasked with ensuring that their work is for the benefit of humanity rather than serving narrow interests. Ultimately, as scientists continue to explore these monumental questions about existence, they are compelled to confront these ethical considerations continually. The aim is to promote a pursuit of knowledge that not only expands our understanding of the universe, but also respects and enriches our shared human experience. It's a delicate balance, but one that is essential for responsible scientific inquiry. To unlock the secrets of the early universe, scientists rely on promising technological innovations that enhance our understanding of cosmic events that happened billions of years ago. One of the most significant tools is the advancement of powerful telescopes, specifically those designed to observe distant galaxies and stars. These telescopes, equipped with advanced optics and sensors, can capture light that has traveled across the universe for countless years, revealing crucial information about the formation of the universe shortly after the Big Bang. Another area of innovation is in the field of particle physics, particularly with facilities like particle colliders. These machines smash particles together at incredibly high speeds, creating conditions similar to those found just after the universe began. By studying the resulting reactions and new particles formed in these collisions, scientists can gain insights into the fundamental building blocks of matter and the forces that shape the early universe. Space exploration technology is also essential. Missions sent to observe exoplanets and cosmic phenomena help expand our understanding of conditions that might mimic those in the early universe. For instance, studying the atmospheres of distant worlds can inform us about their origins, which parallels the processes that may have occurred during the universe's infancy. Moreover, the development of computer simulations plays a critical role in this exploration. These simulations allow researchers to model cosmic events, such as the rapid expansion or inflation of the universe, and visualize complex phenomena that we cannot directly observe. The accuracy of these simulations has improved dramatically, contributing to our understanding of early cosmic history. Finally, advancements in gravitational wave detectors have opened a new window into the universe. These detectors can sense ripples in space-time caused by massive events, such as the merging of black holes. Observing these waves can offer clues about extreme conditions and events in the early universe that we may not see through traditional light-based observations. Together, these innovations form a powerful toolkit that helps scientists decode the early chapters of our universe's story, allowing us to explore questions about its origins, structure, and evolution. With each technological leap, we edge closer to understanding the mysteries that have fascinated humanity for centuries. Innovations in various fields have a significant ripple effect on cosmological research, enhancing our understanding of the universe. For instance, advancements in technology often provide astronomers with powerful new tools. Take imaging technology, for example. The development of high-resolution cameras allows scientists to capture more detailed images of celestial objects. This precision leads to better analysis, helping researchers comprehend the formation and behavior of galaxies, stars, and planets. Moreover, data analysis techniques borrowed from computer science, such as machine learning, are transforming how vast amounts of astronomical data are processed. By utilizing algorithms designed to find patterns or anomalies, researchers can sift through countless images and measurements more efficiently than ever before. This means faster discoveries and a deeper understanding of phenomena once thought too complex or subtle to detect. Another area of influence is materials science. Innovations in the creation of lightweight, durable materials have led to the development of advanced telescopes and spacecraft. These instruments can operate in challenging environments like space where conditions are extreme. Enhanced materials allow missions to be more ambitious, reaching farther into the cosmos and gathering essential data about otherwise inaccessible regions. Even fields like biology and medicine play a role. The study of extremophiles, organisms that thrive in extreme conditions on Earth, provides insights that can inform the search for life on other planets. Understanding how life adapts and survives in harsh environments can guide astrobiologists in exploring whether life might exist in similarly extreme locations beyond our planet. The interplay of various fields with cosmological research leads to new perspectives and possibilities. As techniques and technologies continue to evolve, they create a dynamic landscape where ideas cross boundaries, pushing our understanding of the universe forward in exciting and transformative ways. The concept of the universe's creation from nothing has inspired many cultural works across various forms of art and storytelling. One of the most prominent examples is found in religious texts, where the act of creation often emphasizes a divine being bringing forth the universe from a state of void. For instance, in the book of Genesis from the Bible, the story begins with the assertion that the universe was created by a singular divine command, illustrating the transition from emptiness to existence. In literature, the concept has appeared in various narratives. The classic novel The Hitchhiker's Guide to the Galaxy by Douglas Adams humorously explores the idea of creation through a mix of science fiction and whimsy, suggesting that the universe emerged like a cosmic accident, with life evolving in unpredictable ways. In film, the visual representation of creation from nothing is most vividly depicted in works like 2001: A Space Odyssey. This movie presents the dawn of humanity and the exploration of evolution through spectacular visuals that evoke the mystery of existence, highlighting how beings can arise from primal chaos. Additionally, in the realm of visual arts, paintings such as The Creation of Adam by Michelangelo capture the moment of creation with stunning artistry, providing a symbolic interpretation of divine creation, emphasizing the relationship between the creator and the created. The concept also resonates in contemporary scientific documentaries and discussions, where filmmakers and writers depict the Big Bang theory. These works explain how the universe expanded from a singular point, often using engaging visuals and clear narratives to present the idea of a dynamic and ever-evolving cosmos emerging from a once empty existence. These diverse cultural works reflect humanity's ongoing fascination with the origins of the universe, displaying our quest for meaning and understanding regarding our place within it. Each interpretation brings its own flavor, encouraging viewers and readers to ponder the profound mystery of existence itself. Popular media has played a significant role in shaping public understanding of cosmological theories. Through films, television shows, books, and documentaries, concepts like the Big Bang, black holes, and the nature of the universe have entered mainstream conversations. These forms of media often simplify complex scientific ideas, making them accessible and engaging for a wider audience. For instance, movies like Interstellar and series such as Cosmos introduce concepts such as time dilation and the vastness of space, captivating viewers' imaginations while providing a gateway to deeper understanding. While they may take creative liberties, these stories spark curiosity and encourage people to explore the science behind them. Moreover, social media platforms allow for rapid dissemination of knowledge. Public figures, scientists, and educators use these channels to clarify misconceptions and share the latest research in cosmology. This immediate access helps demystify complicated topics, although it can sometimes lead to the spread of misinformation when ideas are misrepresented or oversimplified. Overall, the influence of popular media is profound. It acts not just as a vehicle for entertainment, but also as an educational tool that ignites interest in the scientific inquiry of the cosmos, inviting people to question and seek answers about the universe we inhabit. This blend of inspiring storytelling and accessible education encourages a deeper appreciation for the complexities of cosmology. Communicating complex cosmological ideas to the general public can be an exciting challenge. The key lies in relating those grand concepts to everyday experiences. Start with simple comparisons or analogies that people can grasp. For instance, when explaining the vastness of space, one can compare the universe to an incredibly large balloon, where every dot represents a galaxy. As the balloon inflates, the dots move further apart, illustrating how galaxies are racing away from each other. Visual aids are incredibly valuable, bringing abstract ideas to life. Diagrams, animations, or even simple illustrations can help clarify concepts such as black holes or the expansion of the universe. For example, depicting a black hole as a funnel can show how it draws in anything nearby, making it easier for people to conceptualize its gravitational pull. Storytelling also plays a pivotal role. Narratives about astronomers, scientists, or missions can engage audiences emotionally. Sharing the journey of human discovery, the triumphs and even setbacks in understanding the universe can resonate deeply. Using clear and relatable language is essential. Avoid technical jargon unless it's neatly explained. Instead of discussing gravitational waves, talk about ripples in space caused by massive objects moving, which reveals the same concept in an accessible manner. Finally, encourage questions and curiosity. Creating an open dialogue transforms passive listeners into active participants. When people feel a connection to the topic, whether through relatable examples, engaging stories, or interactive discussions, they are more likely to grasp and retain complex cosmological concepts. To effectively dispel myths about the universe emerging from nothing, science communicators can begin by clarifying what nothing really means in this context. Traditionally, nothing is understood as the absence of anything, no matter, no energy, and no space. However, in the realm of modern physics, particularly quantum mechanics, nothing can be more complicated. Scientists suggest that even in empty space, there can be fleeting energy fluctuations. These fluctuations have the potential to create particles, which might lead to the rapid expansion of energy we associate with the Big Bang. This process can mislead people into thinking that something came from absolute nothingness. Effectively communicating these concepts means using relatable analogies, such as comparing it to a calm surface of water where tiny ripples can suddenly appear. To counter misconceptions, it is also vital to clarify that the universe did not simply pop into existence without cause. Theories suggest that the universe originated from a singular point, a state of extreme density and temperature. This foundation sets the stage for everything we see today. By explaining these ideas with patience and in engaging ways, communicators can foster a deeper understanding of the universe's origin. Moreover, it is essential to highlight the distinction between scientific theories and popular interpretations. Many myths stem from oversimplifications of scientific ideas when they are shared in media or popular discussions. Thus, using clear language and straightforward examples can help audiences differentiate between the awe-inspiring yet complex truths of the cosmos and the myths that often arise from misinterpretations. Through careful explanation and by addressing common misunderstandings, science communicators can build a more accurate narrative of our universe's beginnings, making the wonders of science accessible and engaging to all. Speculative theories about alternate realities beginning from a state of nothing often explore ideas related to quantum physics and cosmology. Imagine a vast emptiness where there is no matter, energy, or even space as we know it. From this void, one popular theory suggests that fluctuations in quantum fields could cause tiny bubbles of energy to form. This energy might expand rapidly, creating new universes or realities that diverge from one another in unique ways. One intriguing concept is that these new realities could develop distinct laws of physics, potentially allowing for entirely different forms of matter or energy. By initiating from nothing, one does not just witness the birth of a single universe. Instead, countless alternate realities could spring into existence, each with its own characteristics and history. These alternate worlds might operate independently, yet some theorists wonder if they could ever influence one another, possibly through interactions at the quantum level. Another fascinating notion relates to the idea of a multiverse. Here, our universe is just one bubble in a larger cosmic foam, where each universe has branched off from others through processes akin to cosmic evolution. In each instance, the pathways taken might lead to differing outcomes, resulting in alternate realities with worlds very much unlike our own. Moreover, these scenarios compel us to reconsider the concept of time. In an endless sea of alternate realities, decisions and events could unfold in myriad ways, suggesting that every choice creates a new branch. Each reality could coexist simultaneously, with some echoes of our decisions reflected in different universes. Thus, the dream of nothing transforms into an expanse of infinite possibilities, blurring the line between creation, choice, and existence itself. The idea of alternate realities, also known as parallel universes, invites us to reconsider what we know about the universe's origin in fascinating ways. When we think about our universe, we often imagine it as a singular, vast space where everything we see is located. However, alternate realities propose that there may be countless other universes operating alongside ours, each with its own distinct properties and laws. This notion enriches our understanding by suggesting that the cosmos is far more complex than a single story. Imagine our universe as one page in a book. Each alternate reality could represent another page, each telling its own tale with unique characters and events. This perspective helps simultaneously address the question of why our universe is structured the way it is. If many other universes exist, it makes sense that ours, with its specific conditions allowing for life, would be just one possibility among many. This concept also challenges our understanding of cause and effect, suggesting that for every choice or event, there could be a branching pathway creating new realities. When we consider monumental moments like the Big Bang, the idea of alternate realities implies that they could stem from different configurations of that critical event, leading to various outcomes in different universes. Exploring alternate realities pushes scientists and thinkers to extend their imagination, prompting deeper inquiries into our own existence. If various realities exist, it raises questions about the nature of time, space, and whether life as we know it fits into a much larger cosmic narrative. We were once limited by what we could observe, but the idea of parallel universes helps us to consider what lies beyond our observable boundaries, fundamentally altering our understanding of where we come from and what the universe might still hold. Enhancing scientific literacy plays a crucial role in improving public engagement with cosmological research. When individuals understand basic scientific concepts and methods, they can appreciate the discoveries and challenges within the vast universe. It's like opening a door to a room full of wonders, where knowledge allows people to explore beyond the surface. With a solid grasp of science, the public can critically think about complex issues such as dark matter, the expansion of the universe, or the possibility of other life forms. This understanding builds a connection, transforming abstract ideas into relatable ones. For example, when people learn how telescopes gather light from distant galaxies, they begin to see the universe not just as a collection of stars, but as a dynamic and intricate system full of mysteries. Moreover, when scientific literacy increases, it fosters dialogue. People become more willing to ask questions and discuss findings, whether in casual conversations or on larger platforms. This inquisitiveness encourages scientists to share their knowledge in ways that are accessible and engaging, bridging the gap between research communities and the public. A well-informed public also becomes more empowered to engage with topics like space exploration funding and climate change, issues that have significant implications for society. When citizens grasp the importance of cosmological research, they are more likely to support policies and initiatives that promote further investigation into the universe. Improving scientific literacy not only enhances individual understanding but also cultivates a culture where curiosity is encouraged and scientific exploration is celebrated. The outcome is a more engaged society, actively participating in the quest to understand our universe. Educational institutions serve as vital hubs for expanding our understanding of the universe's evolution. They create an environment where curiosity thrives, encouraging students and the wider community to explore fundamental questions about our existence. Through structured curriculums, schools and universities impart foundational knowledge in astronomy, physics, and related sciences, helping students grasp complex concepts about the universe's origins, structure, and future. Beyond traditional classrooms, educational institutions often host workshops, seminars, and public lectures featuring expert scientists and researchers. These events bring the latest discoveries in cosmic studies to the community, making complex ideas more accessible. By engaging with cutting-edge research, individuals can better appreciate the universe's past, such as the Big Bang theory, the formation of galaxies, and the life cycle of stars. Moreover, educational institutions foster collaboration and innovation through research programs. Students and faculty often participate in astronomical research, contributing to discoveries and technological advancements such as new telescopes and exploration missions. This hands-on experience deepens understanding and instills a sense of stewardship for our universe. Additionally, institutions play a crucial role in outreach programs, partnering with local organizations and schools to inspire younger generations. Exciting activities like stargazing nights, planetarium shows, and science fairs generate interest and wonder about the cosmos. By making astronomy engaging, they help cultivate future scientists and informed citizens who understand the universe's ongoing evolution and our place within it. Ultimately, educational institutions are not just places of learning. They are beacons of knowledge that illuminate the complexities of the universe, inspiring a shared fascination that can lead to a broader appreciation of the cosmos and our responsibilities within it. Fictional narratives about the universe's origin often weave together real scientific theories with imaginative storytelling. At the heart of many of these tales is the Big Bang theory, which suggests that the universe began as a hot, dense point that expanded rapidly. This idea serves as a rich backdrop for plots about creation and transformation, allowing authors to explore how everything we know, from galaxies to individual stars, came from a single moment of explosive energy. Writers frequently take inspiration from concepts like cosmic inflation, which explains how the universe expanded so quickly after the Big Bang. In fictional works, this might be depicted as a sudden burst of new worlds or realms appearing all at once, filled with diverse life forms. These imaginative interpretations can lead to fascinating scenarios, such as worlds with unique physical laws or alien civilizations that evolved in the wake of this cosmic event. Moreover, narratives may introduce elements like dark matter and dark energy, two mysterious components of our universe. While scientists acknowledge that these forces shape the universe's structure and expansion, fiction often exaggerates their properties. This leads to plots where unknown forces tangibly affect the lives of characters, showing how these scientific questions of our existence can become dramatic storytelling devices. Character journeys through time and space can also draw on the concept of the multiverse, a theory suggesting that our universe might be one of many. In fiction, this can translate into parallel worlds or alternate realities, offering endless possibilities for adventure and conflict. Characters may experience lives that diverge based on different choices in these parallel universes, probing deep philosophical questions about fate and free will. By combining these scientific concepts with imaginative plots, fictional narratives create a bridge between fact and fantasy. They spark curiosity about actual scientific theories while providing an engaging way to explore fundamental questions about existence and our place within the cosmos. These stories keep audiences fascinated, encouraging them to think about the universe's mysteries long after they've turned the last page or watched the final scene. Speculative fiction often serves as a fascinating lens through which we can explore complex ideas about the universe and our place within it. Through stories that stretch the imagination, we are given the freedom to consider possibilities that go beyond current scientific understanding. This genre often contemplates themes such as the nature of existence, the limits of technology, and the ethical implications of space exploration, helping to illustrate crucial lessons that can inform our understanding of cosmology. One significant lesson is the importance of curiosity and the spirit of exploration. Many speculative works remind us of humanity's innate desire to push boundaries and seek knowledge. This echoes the real-world pursuit of cosmic understanding, where scientists continually strive to unveil the mysteries of black holes, dark matter, and the formation of galaxies. Furthermore, speculative fiction often highlights the interconnectedness of life within the universe. By imagining civilizations on distant planets or the consequences of alien encounters, these stories encourage us to think about how universal laws apply beyond Earth. They prompt a deeper appreciation for the vastness and complexity of cosmological phenomena, reminding us that while we may see ourselves as distinct, we are also part of something much larger. Another lesson drawn from these narratives is the examination of possible futures. Whether depicting utopias or dystopias, speculative fiction can illuminate the choices we face today, especially regarding technology and environmental sustainability. By envisioning the long-term consequences of our actions, these stories urge us to consider how our current path might shape future generations in both positive and negative ways. Moreover, speculative fiction often delves into the ethical dilemmas associated with advanced technology and space travel, serving as a cautionary tale for real-life scientific advancements. As humanity stands at the brink of significant technological breakthroughs, these narratives push us to reflect on responsibility and the moral implications of our decisions in the cosmos. Comparing speculative fiction with cosmological facts reveals powerful lessons about curiosity, interconnectedness, the power of choice, and ethical considerations in science. These narratives not only expand our imaginations, but also reinforce the importance of grounding our ambitions in thoughtful reflection as we navigate the vast unknowns of the universe. The question of how the universe originated from nothing remains one of the most profound mysteries in cosmology. Although we possess a wealth of knowledge about the universe's expansion and its history, we still grapple with several big questions about its beginnings. One fundamental question is what nothing really means in this context. Is it an absence of everything, including space and time, or is it simply a vacuum that contains potential? Another crucial area of inquiry involves the mechanisms that could trigger the creation of the universe. Some theories suggest that quantum fluctuations might enable the spontaneous emergence of particles from a state of nothingness. If true, this could imply that the universe emerged through natural processes, although the exact details of how this would occur remain elusive. We also consider the role of cosmic inflation, a rapid expansion that occurred shortly after the Big Bang. Some scientists speculate that this inflationary phase could be linked to the universe's origins. However, the specifics of how inflation began and whether it relates to a pre-existing state similar to nothing is still an open question. Moreover, some theories propose that our universe might be just one of many existing in a multiverse. If this is the case, it raises yet another question. What lies beyond our universe? Are we simply one bubble among countless others, each with different properties and laws? Finally, we are left pondering the ultimate fate of the universe. Understanding its origin could shed light on its destiny. Will it continue to expand forever, recollapse, or transform in ways we cannot yet imagine? These questions intertwine as scientists search for not only the story of how everything began, but also for the deeper implications of existence itself. The pursuit of these answers invites us to explore the fabric of reality and the fundamental laws that govern the cosmos. Contemporary cosmologists face an intriguing landscape filled with unanswered questions about the universe. To prioritize these questions in their research agendas, they often consider a blend of scientific importance, observational feasibility, and the potential for groundbreaking discoveries. Firstly, the questions with the most significant implications for our understanding of the cosmos take precedence. For instance, mysteries related to dark matter and dark energy are at the forefront. These phenomena make up most of the universe yet remain fundamentally elusive. Investigating them could reveal profound truths about the very fabric of reality, guiding research efforts and directing resources toward experiments and observations that aim to uncover their nature. Next, cosmologists evaluate which questions can be addressed with available technologies and methods. Some mysteries may be theoretically exciting but remain out of reach due to current limitations in observational capabilities. For example, exploring the very early universe, just moments after the Big Bang, requires advanced telescopes and instruments designed to detect signals from that era. Thus, practical considerations play a crucial role. Moreover, there is a collaborative spirit in the cosmology community. Researchers often share findings and insights, creating an ongoing dialogue that helps to refine priorities. Questions that spark collective interest can rapidly become focal points of research, especially if they encourage innovative approaches or new technologies. In addition, cosmologists pay attention to emerging data, which can shift priorities overnight. As new telescopes begin to operate or as space missions gather fresh information, previously unconsidered questions may move to the forefront. This dynamic nature of research encourages adaptability and responsiveness, ensuring that cosmologists remain aligned with the latest developments in their field. Ultimately, the prioritization of unanswered questions is a complex but fascinating process. By focusing on the most impactful, feasible, and collaborative inquiries, cosmologists strive to unravel the mysteries of the universe, allowing humanity to deepen its understanding of its place in a vast and astonishing cosmos. Skeptical perspectives have played an essential role in shaping the study of the universe's beginnings. When scientists proposed theories about how our universe started, such as the Big Bang, skepticism acted as a critical filter. This questioning encouraged researchers to seek robust evidence and develop stronger, more testable hypotheses. Rather than accepting ideas at face value, skeptics push for a deeper understanding, demanding clarity on how conclusions were reached. For instance, early theories about the universe's origin faced significant scrutiny. Skeptical scientists meticulously examined the evidence from cosmic background radiation, the faint light left over from the Big Bang, which has become a cornerstone of support for this theory. Questions about the data's reliability and interpretation led to advancements in technology and methods for observing the universe. Moreover, skepticism fosters collaboration across different scientific fields. It encourages astronomers, physicists, and cosmologists to work together to approach complex questions from multiple angles. This interdisciplinary dialogue has led to innovative theories and models that enhance our understanding of cosmic evolution. Furthermore, skepticism does not merely challenge existing ideas, it also opens the door to new possibilities. The exploration of alternative theories regarding the universe's beginnings, such as cyclic models or multiverse concepts, has pushed scientists to refine their main frameworks and consider a broader range of possibilities. As a result, skepticism is not just a hindrance, it is a catalyst for growth, fostering a climate where scientific inquiry can thrive and evolve, ultimately leading to more profound insights into the cosmos. Throughout history, skepticism has played a crucial role in advancing our understanding of the cosmos. One compelling example is the transition from the Earth-centered view of the universe to the Sun-centered model. When early astronomers like Copernicus proposed the idea that the Sun, not the Earth, was at the center of our solar system, they faced significant resistance. This skepticism arose from deeply rooted beliefs and observational habits that seemed to support the traditional view. However, as later scientists like Galileo began to use the telescope, they collected evidence that challenged these earlier assumptions. Their willingness to question established knowledge ultimately led to a profound shift in our understanding of space and our place within it. Another example is the discovery of the existence of galaxies beyond our Milky Way. In the early 20th century, many astronomers were skeptical about the idea that there were other galaxies in the universe. Edwin Hubble's observations of distant nebulae, which he showed were actually separate galaxies, dramatically changed this view. His findings also helped to establish that the universe is expanding. This leap from skepticism to acceptance opened new avenues in cosmology and deepened our understanding of the universe's vastness. These historical moments demonstrate that skepticism is not merely doubt, but a powerful tool for inquiry. By challenging established beliefs, scientists can prompt investigations that lead to groundbreaking discoveries. Each instance illustrates how questioning assumptions leads to deeper insights into the workings of the universe, guiding future exploration and understanding. This ongoing cycle of skepticism and discovery is fundamental to the scientific method, showing that curiosity and doubt can illuminate the deepest mysteries of space. Human curiosity has been a fundamental force propelling our quest to understand the universe, especially when contemplating its origins from a state of nothing. This intrinsic desire to explore is rooted in our nature. We ask why and how because we seek to comprehend our place in the cosmos. The concept of the universe emerging from nothing challenges our understanding of existence itself, prompting profound questions about creation, time, and reality. Scientists and astronomers are driven by the mystery of how something as vast and complex as the universe could arise from what appears to be nothing. This curiosity has led to the development of theories that suggest the universe began with a tremendous event, often referred to as the Big Bang. During this event, space and time originated, along with all the matter and energy we observe today. Humans are not just content to know that the universe exists, we strive to unpack the processes that led to its formation. Research in cosmology, particle physics, and quantum mechanics opens up pathways to illuminate these mysteries. For example, scientists explore the idea of a quantum vacuum, which suggests that even in a state where no matter exists, fluctuations can lead to the formation of particles and, consequently, realities. This exploration is fueled by our enduring thirst for answers, where every discovery births further questions, spurring a cycle of inquiry. This human curiosity also manifests in a cultural sense. Throughout history, mythologies and philosophies have sought to explain our existence and the cosmos. Each narrative reflects our need to make sense of the unknown. As our scientific capabilities have grown, so has our ability to investigate these vast cosmic questions with sophistication. Ultimately, the drive to study the universe from nothing highlights our desire to understand the very fabric of existence. It is more than mere scientific pursuit. It is a testament to our collective imagination and a reflection of our quest for meaning in the universe. Through this journey, we gain not just knowledge about the cosmos, but also insights about ourselves as part of this magnificent universe we seek to comprehend. Scientists are not just intellects. They are often driven by personal stories that fuel their passion for understanding the universe. Take the example of a prominent astrophysicist who grew up gazing at the night sky through his father's old telescope. As a child, he found wonder in the stars, understanding their basic positions but yearning to grasp their deeper secrets. Every twinkling light held the promise of a story about how they were born, how they live, and how they will die. That childhood curiosity led him to dedicate his life to studying astrophysics, hoping to inspire others, just as he had been inspired. Another notable story comes from a woman who turned her childhood struggle with dyslexia into a strength. While reading was challenging, visualizing the cosmos through art allowed her to express herself. She took that creative passion into the field of engineering, working on spacecraft that explore distant worlds. Her ability to think outside the conventional bounds turned her into a brilliant innovator in her field, driving her to break barriers in space exploration. She often shares how the beauty of space art continues to motivate her, reminding her that science and creativity are not opposite but complementary. Then there's the story of a physicist who was fascinated by the concept of gravity after watching a leaf fall from a tree as a child. The way it spiraled, caught in the air currents, sparked an interest that grew into a lifetime quest to understand the forces that dictate movement in the universe. His research on gravitational waves has profoundly impacted how we perceive space and time. The thrill of witnessing a ripple in space-time, something he had only read about, was a defining moment for him, showing how personal observation can lead to groundbreaking discoveries. Each of these scientists carries a unique tale, illustrating that the search for understanding the universe springs from deep-rooted curiosity fostered in moments of wonder. Their stories remind us that science is as much about personal experiences and emotions as it is about equations and theories. Global collaborations play a crucial role in our quest to understand the universe's origins. When scientists from different countries and cultures come together, they bring diverse perspectives, expertise, and resources. This united effort allows for sharing groundbreaking ideas that might not emerge in isolated environments. For instance, a discovery made in one corner of the world can inspire researchers elsewhere to extend that knowledge further or explore different angles of inquiry. Such collaborations often lead to larger projects that no single nation could undertake on its own, like space telescopes or particle accelerators. These complex instruments need vast expertise and significant funding. By working together, countries pool not only their financial resources but also their technical skills, creating more advanced tools to probe the mysteries of the universe. Additionally, global teams contribute to the creation of a shared scientific language. This unifying aspect is critical when navigating the complexities of discussing concepts like dark matter or cosmic evolution, which can be abstract and difficult. As researchers communicate more effectively, they refine their ideas and achieve clarity that facilitates further discoveries. Furthermore, global collaborations promote access to data and findings across borders. When teams freely share their data, it accelerates the pace of research. For example, an observation made by one team can lead to new questions for another, generating a chain reaction of discovery that helps illuminate the universe's beginnings more profoundly. By uniting their strengths, scientists worldwide enhance our collective effort to uncover the universe's secrets. Their collaboration enriches knowledge, fosters innovation, and ultimately brings us closer to understanding how everything began, a quest that is at the very heart of human curiosity and scientific advancement. Throughout history, diverse cultures have crafted unique perspectives on the cosmos, enriching our understanding of the universe in fascinating ways. Each culture adds a different lens through which to view the stars, planets, and the very nature of existence. For instance, ancient civilizations like the Mayans had intricate calendars based on astronomical events, allowing them to predict celestial occurrences with remarkable accuracy. Their observations taught them how to align agricultural cycles with cosmic events, illustrating a deep connection between the sky and daily life. In contrast, indigenous cultures around the world often weave their myths with the stars, viewing the night sky as a tapestry of stories and teachings. These narratives contribute to a holistic understanding of humanity's place in the universe. For example, Aboriginal Australians see the Milky Way as a river of stars, which informs their navigation and seasonal changes. The spiritual significance tied to these celestial patterns enriches cosmological research by integrating cultural values with scientific knowledge. Additionally, Eastern philosophies, particularly in Buddhism and Hinduism, explore profound concepts like the cyclical nature of time, emphasizing that the universe is in a constant state of rebirth and transformation. This perspective encourages scientists to think beyond linear models of time and existence, considering the universe as a dynamic entity. By combining these rich cultural insights with modern science, researchers can approach cosmology in a more nuanced way. This melding of ideas promotes a broader appreciation of our universe and encourages collaboration and dialogue across disciplines. Different cultures bring not only knowledge but also appreciation for the mystery and beauty of the cosmos, shaping the ongoing quest to understand our place within it. The story of the universe's beginning captivates people far beyond the realm of science because it touches on fundamental questions that all of us ponder. Where do we come from, and how did everything begin? The concept of the Big Bang, which proposes that our universe originated from an incredibly hot and dense point and has been expanding ever since, is not just a scientific idea, it invites thoughts about existence itself. This narrative offers a glimpse into the vast mysteries of life, igniting curiosity about what space is, how time came to be, and what might lie beyond our observable universe. It creates a bridge between human experience and the cosmos, making it relatable. Every person can look up at the night sky and wonder about the stars and galaxies, fostering a sense of connection to the universe that surrounds us. Additionally, the story of creation encourages contemplation about future possibilities. If the universe has changed and evolved over billions of years, what does that mean for all of us looking ahead? Are we part of a continuous journey, or is there an end to our story? This exploration of beginnings and endings can provoke deep philosophical and spiritual thoughts, resonating with themes of purpose and existence that have long fascinated humanity across cultures and ages. Thus, the universe's origin becomes more than just a scientific concept. It transforms into an epic tale that unites us in a shared quest for understanding, evoking wonder and inspiring hope about our place in the cosmos. Cosmology, the study of the universe and its origins, holds a fascination that can ignite curiosity in anyone. It encourages us to look up at the night sky and wonder about the stars, galaxies, and the vastness beyond our home planet. This sense of wonder is powerful. It invites questions that have puzzled humanity for centuries. For young minds, these cosmic questions can serve as a gateway to creativity, critical thinking, and scientific exploration. When we talk about the universe's beginnings, its expansion, or the nature of black holes, we open doors to understanding the fundamental laws governing reality. Each discovery in cosmology reveals more about who we are and where we fit within this seemingly infinite tapestry. By showing students and young explorers the beauty and complexity of the cosmos, we can inspire them to delve deeper into science, technology, engineering, and mathematics, disciplines that play vital roles in unraveling cosmic mysteries. Furthermore, The collaborative nature of cosmological research highlights the importance of teamwork and diverse perspectives. When future generations see scientists from around the world working together on projects like telescopes or space missions, they learn that addressing big questions requires collaboration and an open mind. This not only fosters innovation, but also cultivates a sense of global citizenship. With the rise of inspiring space missions, images of distant galaxies, and the concept of life existing elsewhere in the universe, the intrigue continues to grow. Young people are encouraged to dream about what lies beyond and consider careers in which they can be part of that exploration. By sharing the excitement of scientific breakthroughs and the ongoing quest to understand the universe, we nurture a generation ready to think boldly, ask deeper questions, and tackle challenges that we have yet to imagine. In this way, the wonder of cosmology not only enriches our knowledge, but also paves the way for a brighter, more inquisitive future. Research on the concept of a universe arising from nothing challenges our traditional understanding of how existence begins. Imagine an empty space, devoid of matter or energy. The idea suggests that out of this void, the universe might have spontaneously emerged. Scientists discuss that this nothing isn't a complete absence of everything, but rather a state where the laws of physics, such as fluctuations in energy, can still operate. One key takeaway is that quantum mechanics plays a significant role in this discussion. In quantum theory, particles can appear and disappear in empty space. This suggests that, even in what we perceive as nothing, there are event layers where reality can manifest unexpectedly. Another vital point is the notion of energy conservation. Although we think of energy as needing a source, the universe itself may exemplify a system where energy can arise from fluctuations. Additionally, the origins of space and time come into question. In this framework, space and time as we know them might not have existed prior to the universe's birth. This can lead to the idea that the universe's creation was not bound by the constraints we typically associate with cause and effect. This discussion opens up exciting possibilities for how we perceive existence, leading to a broader contemplation of what reality encompasses. While it remains a complex and speculative area of research, the investigation into a universe from nothing invites us to rethink fundamental questions of existence and our place within the cosmos.